Take a moment to notice where you are right now. Maybe you're lying in bed, the lights dim, your body heavy after a long day. Your eyes might be half closed, searching for that quiet space where thoughts loosen their grip. Perhaps you feel a bit restless, as if your mind still wants to wander while your body asks for rest. Or maybe you're already sinking into that soft, in-between place where waking and dreaming overlap. Wherever you are in this moment, allow yourself to pause. Allow yourself to breathe and simply be. You pressed play on this video for a reason. Not because you needed noise, but because you wanted something different. A voice to guide you. To remind you that the world is vast, mysterious, and bigger than the small circle of worries that follow us into the night. You're here to listen, to drift, to let curiosity carry you toward rest. Tonight, we'll explore one of the most profound and inevitable truths of existence: entropy. The quiet law of disorder, the hidden current beneath everything you see and touch. It's the reason why ice melts, why stars burn out, why civilizations rise and fall. It's the invisible tide that ensures nothing stays still forever. But don't worry, this won't be a cold science lecture. You don't need equations to understand entropy. You already live it every single day. When you walk into a messy room, when your hot coffee cools, when your thoughts scatter before sleep, you're watching entropy at work. This journey will not only be about physics, but about life itself. About you, me, and the strange universe we all belong to. As you listen, you don't need to stay awake. If sleep comes, let it. Entropy will still unfold, whether your eyes are open or closed. My words will weave themselves into your dreams, carrying you gently forward. Let's begin with something simple: your breath. Each inhale brings order. Oxygen flows into your lungs, into your blood, into your cells. Each exhale releases carbon dioxide, a little more chaos returning to the air. Even in this simple cycle, you can feel the balance. Life is a constant negotiation with entropy. We gather energy to build, to move, to think, and slowly, inevitably, we release it back to the world. Now think about your body, lying where you are. Your muscles are tired, your heartbeat steady, your skin warm. Inside you, trillions of cells are buzzing, working, fighting, repairing. They're holding back entropy for as long as they can, building little islands of order in a vast ocean of disorder. And yet, no matter how strong they are, entropy is patient. It waits. It always wins in the end. But that doesn't have to be frightening. In fact, it can be beautiful, because entropy isn't just destruction. It's also change. It's transformation. It's the reason the stars that once collapsed in fiery explosions scattered the elements that became your bones, your blood, your thoughts. Without entropy, there would be no galaxies, no Earth, no life. Without entropy, the universe would be a frozen, lifeless crystal, perfectly still and perfectly empty. So tonight, as you listen, think of entropy not as an enemy, but as a companion. It is the quiet storyteller of the cosmos. It turns every ending into a beginning. It ensures that nothing is wasted, that everything flows. Imagine the universe billions of years ago. When it was young, a hot, dense fireball expanding into the unknown. Back then, entropy was low, surprisingly low. Matter clung together, energy moved in neat patterns. But as the universe expanded, order gave way to variety, and variety gave way to complexity, and complexity to the messy, vibrant reality we now call home. Every star in the night sky is a monument to entropy. Every human story, every memory, every love, every loss, all of it unfolds under this quiet law. And now, here you are, one small piece of this grand puzzle, listening, breathing, drifting. Your life too is part of entropy's tale, a flame burning for a short time, giving warmth and light before it fades. And yet, even after it fades, its energy lingers. Scattered into new forms, new stories, new beginnings, as you lie here. Notice how the weight of your body presses into the surface beneath you. Notice how the air moves in and out of your lungs. The simple truth is this: you are not separate from entropy. You are entropy. You are the living evidence of the universe unfolding, reshaping, scattering, gathering again. Your thoughts, your heartbeat, your warmth, they are the ordered dance that exists only because disorder is always waiting at the edge. This video will take you deeper into that mystery. We'll explore how entropy shapes time, why it decides the direction of the future, how it sculpts galaxies, how it whispers through the collapse of stars. We'll wander into philosophy, into human history, into the fragility of life. And through it all, we'll see that entropy isn't something to fear. It is the most honest law of the universe, and perhaps the most comforting one. So, as you continue listening, allow yourself to let go. Let go of the day that has passed. Let go of tomorrow's demands. Let go of control. Like everything else, you too can rest in the flow of entropy, knowing that nothing lasts, but nothing is ever truly lost. Close your eyes if they're not already closed. Sink into the rhythm of your breath. You are safe. You are part of the endless unfolding. And together, we are about to wander into the heart of entropy, the ultimate law of the universe. Before we step too far into cosmic mysteries, let's pause and ask a simple question. What exactly is entropy? It's a word that can sound intimidating, heavy with equations and symbols. But at its heart, entropy is something we've all seen, touched, and felt. It's the way your hot tea slowly cools down on the table. It's the way cream swirls into coffee until the colors blend and the patterns vanish. It's the way a tidy room, left alone, eventually gathers dust, clutter, and disorder. Entropy is often called the measure of disorder. But that's only the beginning. It's better to think of it as a measure of possibility. Imagine a pack of cards. If all the cards are neatly stacked in order, ace through king, there's only one very specific way that deck can exist. That's low entropy. But if you shuffle the cards, suddenly there are countless possible arrangements. Almost all of them look messy. That's high entropy. The more ways something can be arranged, the more likely it is to drift toward disorder, and that, in its simplest form, is entropy, the natural pull toward what is most probable. Now, here's the remarkable part. Entropy is not just a concept. It is one of the fundamental laws of the universe. Physicists call it the second law of thermodynamics. This law says, in any closed system, entropy always increases. Always. No exceptions. Think about that for a moment. Every fire that burns, every breath you take, every star that shines beneath it all, entropy is increasing. Energy spreads out. Order dissolves into chaos. The universe is always drifting, one step at a time, toward more probable, more disordered states. But why should this be true? Why should the universe favor disorder over order? The answer is hidden in probability. Order is rare. Disorder is abundant. Picture a box filled with gas molecules. If all the molecules happen to cluster in one corner, that would look very ordered. But the odds of them arranging themselves like that are astronomically small. Instead, the molecules bounce around, spread out evenly, filling the box. That is the natural state because there are far more ways for the gas to be spread out than to be clustered. This isn't about intention or purpose. It's not that the universe wants disorder. It's simply that disorder is overwhelmingly more likely. Entropy also gives us something else. Something deeply human. The arrow of time. Why do we remember the past, but not the future? Why does spilled milk never leap back into the glass? Why does life move forward and never backward? Entropy provides the answer. The past is always more ordered than the future. Once order dissolves, it almost never spontaneously returns. A glass shatters, but the shards do not reassemble. Your body ages, but it never truly grows young again. Heat flows from hot to cold, never the reverse. Time itself, the feeling of before and after, emerges because entropy increases. The direction of time is the direction of entropy. But let's bring it back to you, lying here, listening. Entropy is not some distant principle locked away in textbooks. It's in your body right now. When you eat, your cells capture order from food and turn it into energy. When you breathe, your lungs spread oxygen through your blood, balancing high and low concentrations. Even as you lie still, heat is radiating outward from your skin. Tiny particles of warmth slipping into the air around you. You are a living island of order, surrounded by a universe of growing entropy. But even you, even life itself, cannot escape the law. We resist entropy for a while, organizing, building, thinking, dreaming, but in the end, we join it, and there is something strangely comforting in that. Truth. When the physicist Rudolf Clausius first coined the term entropy in the 19th century, he meant it as a precise mathematical quantity. He used it to explain why heat engines machines like steam engines could never be perfectly efficient. No matter how well you build a machine, some energy is always lost. Some heat always escapes. Entropy always increases, but over time, entropy became more than a scientific term. It became a metaphor for life itself. A reminder that nothing lasts forever, that perfection is fleeting, that every system, whether it's a star, a city, or a single thought, eventually gives way to change. And yet, here's the paradox. If entropy were not real, nothing would exist at all. Without entropy, stars would not burn, galaxies would not form, atoms would never combine, life would never arise. Entropy may bring endings, but it also brings beginnings. Think of it this way. When you strike a match, you release energy. The flame burns, heat escapes, entropy rises. At first glance, that looks like loss. But that energy, that spreading heat, can warm a room, cook a meal, or ignite 1,000 more fires. Entropy does not erase. It transforms. Every ending it creates is also an opening for something new. So as we start this first chapter, keep this in mind. Entropy is not an abstract rule. It is the most intimate companion of your existence. It is the reason you are breathing. It is the reason the stars shine. It is the reason there is time, memory, and story. Entropy is not just about disorder. It is about possibility. It is the great balancing act of the cosmos, ensuring that nothing stays trapped in one state forever. And as you drift further into this journey, let the thought settle in your mind that you, in this very moment, are part of entropy's unfolding. Your warmth, your breath, the steady beating of your heart, all of it is woven into the fabric of this universal law. Entropy is the quiet tide beneath everything, and we are all carried by its current. Think back to your earliest memory of order giving way to disorder. Maybe it was as simple as stacking blocks when you were a child. You built them carefully, one on top of the other, forming a tower that seemed impossibly tall. But with a single nudge and elbow, a tremor, a breath, the tower fell. In seconds, all the care and precision collapsed into a scattered pile. That was entropy. You didn't know the word back then, but you felt its truth. It takes effort to build, but only a moment for things to fall apart. And this isn't just true for blocks. It's true for everything. Consider the food in your kitchen. Fresh fruit, bright and fragrant, slowly softens and spoils. Bread goes stale. Milk turns sour. This is entropy at work. Energy dispersing, molecules breaking down, order dissolving into a state that is more probable. More disordered? Or think of a freshly cleaned room. The surfaces are smooth, the floor uncluttered, everything in its place. But over time, without constant attention, dust gathers, items scatter, clothes pile up. The natural drift is toward disorder. This is why entropy has been called time's fingerprint. It is the quiet signature that every passing day leaves on our world. But entropy isn't just physical, it is also emotional. Have you ever noticed how memories fade? That a crystal clear picture of yesterday becomes blurry with time. The human brain is not immune to entropy. Connections weaken, details scatter, stories we once held tightly begin to drift. Even in thought, order is temporary, and yet the fading of memory makes room for imagination, for dreams, for new stories to form. Just as a forest fire clears space for new growth, the entropy of the mind allows life to move forward. Now expand your vision beyond your home, beyond your body, beyond your mind. Entropy is not only a household law, it is cosmic. Look at the stars. Each one is a furnace of fusion, a delicate balance between gravity pulling inward and nuclear reactions pushing outward. Stars burn because they are dispersing energy, releasing heat and light into the void. That's entropy on a galactic scale, but stars cannot burn forever. Their fuel runs out. Entropy takes over. Some collapse into white dwarfs, some explode into supernova, scattering their elements across space. The calcium in your bones, the iron in your blood, the oxygen in your lungs, these were all born in stars that succumbed to entropy billions of years ago. You are, in the most literal sense, a child of entropy. Entropy also shapes time on the largest scale imaginable. The fate of the universe. Physicists believe the cosmos is moving toward a state called heat death. Oh, it sounds dramatic, but it is simply the ultimate victory of entropy. A time when energy is so evenly spread, so thoroughly dispersed, that nothing new can happen. No stars, no galaxies, no motion, just quiet equilibrium. It is not a tomorrow or even a billion tomorrows away. It is a vision of the farthest future imaginable. And yet, even this distant idea reminds us of entropy's power. It is the universal clock ticking silently forward, guiding everything from your breath to the destiny of galaxies. But let's not get lost in the far future. Let's return to you, lying there, breathing. Entropy is not just about endings. It is about the space between. It is about the transformations that make life possible. Your body is a perfect example. Every cell you carry is a small miracle of order, proteins folding precisely, DNA storing intricate instructions, membranes separating one world from another. But this order is fragile. It requires constant input of energy, food, sunlight, rest. Without it, entropy rises and the system fails. That is why you eat. That is why you sleep. That is why you breathe. You are not defying entropy. You are negotiating with it. Each moment of life is a temporary balance, a postponement of inevitable disorder, purchased with energy borrowed from the world. Around you, there is something humbling in this. We often imagine ourselves as masters of the world, building cities, inventing machines, charting the stars. But entropy reminds us that we are part of a larger current, a flow that no amount of effort can fully resist. Buildings crumble, machines wear down, civilizations rise and fall. And yet, this is not despair. This is the rhythm of life. Without entropy, there would be no change, no growth, no history. A world without entropy would be a frozen, lifeless place. Entropy is not destruction, it is motion. It is the reason rivers carve valleys, the reason clouds drift and break, the reason fire flickers and dies. It is the reason you are alive tonight, listening, drifting, feeling the weight of the day dissolve into the quiet of the evening. Think for a moment about music. A perfect silence is like low entropy. Nothing is moving. Then a song begins. Notes rise and fall, harmonies form and dissolve. Each sound spreads into the air, fading, dispersing, impossible to capture again exactly as it was. That is entropy in action. Music exists because it disappears. And isn't that true of life as well? Moments matter precisely because they cannot last. Love, laughter, sorrow, joy, they all pass through us, leaving traces but never staying fixed. Entropy ensures that life is always moving, always flowing, always becoming something new. So, the next time you sip tea that has grown cold or find dust on a shelf you just cleaned, or watch the colors of a sunset fade into night, remember this: you are not witnessing failure. You are witnessing the universe at work. Entropy is not the enemy of order. It is the partner of order. Without it, there could be no creation, no transformation, no story. It is the quiet law beneath everything: your body, your memories, the stars, and the very fabric of time. And as you let that thought settle, feel yourself becoming part of that flow. Your breath, your warmth, your heartbeat, all of it is woven into entropy's song. And for this moment, in this stillness, you are listening to the most ancient rhythm of the universe. When most people hear entropy, they imagine the fate of stars, the cooling of coffee, or the collapse of order into chaos. But entropy has another identity, one that emerged in the mid-20th century and changed not only physics, but communication, technology, and even our understanding of thought itself. This is the idea of entropy as information. In 1948, Claude Shannon published a paper that laid the foundation of modern information theory. His interest wasn't in thermodynamics, was in how to send messages across noisy channels. Yet the mathematics he used mirrored those of statistical mechanics. Shannon defined the entropy of a message source as a measure of uncertainty. The more unpredictable the message, the higher its entropy. If a source always sends the same letter, entropy is low because no new information is gained. But if every symbol is equally likely, entropy is maximized. Every signal carries the maximum possible information. This parallel was not an accident. Both thermodynamic entropy and informational entropy quantify the distribution of possibilities. In physics, the possibilities are microstates of atoms. In communication, they are symbols or bits. The equation looks strikingly familiar. Asterisk, this is Shannon entropy, where pip_ippy represents the probability of a symbol. Compare it to Boltzmann's formula for entropy, and the kinship is unmistakable. The logarithm, the probabilities. The averaging over possibilities, just the same intellectual. Skeleton dressed in different clothes. What makes this connection profound is how it seeds, reshapes our concept of disorder, instead of thinking of entropy only as chaos. We can think of it as uncertainty or missing knowledge. Entropy tells us how much we don't know about a system until it reveals itself. In physics, this could mean not knowing which particular configuration atoms are in. In communication, it means not knowing which word or symbol will appear. In both, entropy represents the gap between what could happen and what has happened. This perspective also explains why entropy and information are often described as two sides of the same coin. When you learn something, say, when a dice roll lands on a 6, you reduce uncertainty. The system's entropy decreases from your perspective because you now know the outcome. The universe hasn't changed, but your knowledge of it has. Entropy here becomes relational, a measure not just of matter and energy, but of meaning and perception. This brings us to a subtle but important idea. Entropy is not only a law of physics, but also a lens on how we, as conscious beings, interact with reality. Every decision, every thought, every conversation is shaped by the balance of what we know and what we don't. The universe may be tending toward greater entropy, But within that current, we constantly carve islands of order, organizing data, building memories, and creating meaning. Life itself can be seen as an engine that temporarily resists entropy by channeling energy to reduce uncertainty. So, whether in the hum of a cooling star or the words flowing through a digital screen, entropy is not just about decay. It is about possibility, probability, and the stories hidden in patterns. To understand entropy is to understand not only physics, but the very structure of knowledge itself. When we left part 1, the universe had just emerged from its low-entropy dawn. A near-uniform fog of matter and radiation filled the expanding cosmos, smoothed by inflation and marked only by minuscule fluctuations in density. To the human eye, that universe would have looked dull, featureless, almost boring. But hidden within that plainness lay the seeds of everything that would come. Entropy was poised to increase, and with gravity as its ally, the cosmos was about to blossom into complexity. The cosmic microwave background, a snapshot of entropy's youth. One of the most striking pieces of evidence we have about this early era is the cosmic microwave background (CMB). Discovered in 1965 by Arno Penzias and Robert Wilson. The CMB is the faint afterglow of the Big Bang, now cooled to just 2.7 Kelvin above absolute zero. It fills the universe uniformly, like an invisible sea of microwaves. But if you look closely, very closely, you find tiny ripples in the CMB. Variations in temperature of just 1 part in 100,000. These ripples are the fingerprints of quantum fluctuations stretched by inflation. The very imperfections that gravity would later amplify into galaxies, stars, and planets. From the perspective of entropy, the CMB represents a snapshot of a universe still in relative simplicity. It was hot, smooth, and dense, but poised for change. The small irregularities were enough to spark the cascade of structure formation, driving entropy upward as clumps of matter began to coalesce. The first billion years entropy in action, after about 380,000 years. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. With free electrons gone, photons could travel freely through space, giving us the CMB. This period is sometimes called the Cosmic Dark Ages, because the universe was filled with hydrogen gas but had no stars yet to light it up. During this dark era, gravity worked quietly, pulling denser regions of gas into slightly larger clumps. Over millions of years, these clumps grew, attracting more matter and heating as they collapsed. Eventually, the first stars ignited, unleashing light into the darkness. This was entropy at work on a grand scale. Uniform gas clouds represented limited configurations, kind of simplicity. But when gravity pulled gas into stars, galaxies, and superclusters, the number of possible microstates multiplied enormously. Nuclear fusion within stars produced radiation, which spread outward into space, dispersing energy and raising entropy further. The first billion years of the universe was a time of rapid transformation, the birth of stars, galaxies, and black holes. Entropy surged upward, not as chaos, but as cosmic creativity. Order gave way to complexity, and in that complexity lay the potential for life. Black holes, entropy's extreme expression. Perhaps the most fascinating manifestation of entropy in the universe is the black hole. At first glance, black holes seem to be objects of ultimate order, matter crushed into a singularity, all structure erased. Yet physics tells us that black holes represent the highest entropy state known. The reasoning comes from the work of physicist Jacob Bekenstein and later Stephen Hawking. They showed that the entropy of a black hole is proportional not to its volume, but to the surface area of its event horizon, the boundary beyond which nothing can escape. This entropy is immense. A single black hole can hold more entropy than all the stars in the observable universe combined. Why is this so? because a black hole hides information. Everything that falls into its gas, stars, even light loses its unique identity, leaving only mass, spin, and charge behind. From the standpoint of microstates, this is the ultimate disorder. Countless possible configurations reduced to a featureless horizon, dots as the universe evolves. Black holes play a central role in driving entropy upward. They are the engines of entropy, the great sinks where complexity ends and disorder reigns supreme. Galaxies' islands of entropy, growth zoom out, and you find that the universe is not randomly sprinkled with stars. Instead, matter organizes itself into galaxies' immense cities of stars, bound together by gravity. Each galaxy is a laboratory of entropy. Stars within galaxies burn nuclear fuel, releasing heat and radiation into space. Supernova explode, dispersing heavy elements that enrich the interstellar medium. Black holes and galactic centers consume matter and flare with powerful jets. All of these processes increase entropy by dispersing energy and information. But galaxies also illustrate a paradox. To human eyes, a galaxy appears ordered and beautiful, a spiral with arms or an elliptical cloud of stars. Yet from the perspective of entropy, this apparent order masks a deeper disorder. A galaxy has far more microstates than a smooth gas cloud. Its beauty is the byproduct of entropy's relentless rise. Entropy and the chemistry of life, the stars, in their burning, do more than raise entropy. They forge the elements of life. In their cores, nuclear fusion produces carbon, oxygen, nitrogen, and iron. When stars die in supernova, these elements scatter across space, enriching gas clouds that will form new stars and planets. Entropy drives this cycle. The ordered hydrogen in stars fuses into heavier nuclei, releasing energy that radiates outward, spreading disorder into the cosmos. Without entropy, there would be no energy flow, no star formation, and no chemistry. And without chemistry, there would be no life. This connection between entropy and life is profound. Life in its essence is a local decrease in entropy, a small island of order maintained by exporting entropy into the environment. Plants absorb sunlight and release heat. Animals consume food and radiate waste energy. Planets maintain climates by balancing incoming and outgoing energy. The entire biosphere functions as a delicate dance with entropy, feeding on its increase while sustaining fragile order. But all of this begins with the universe's entropy journey. From the Big Bang to galaxies to stars, entropy's increase sets the stage for the emergence of life-bearing worlds. The same law that makes ice cubes melt and coffee cool also makes life possible on Earth. The march toward higher entropy as galaxies formed, stars burned, and black holes grew. Entropy rose steadily. But the story is not static. Entropy is not just about what happens now, it is about the future trajectory of the universe. Today, the universe continues to expand, galaxies drift farther apart, and stars gradually exhaust their fuel. Over billions of years, entropy will continue to increase, driving the cosmos toward new phases. Black holes will dominate, stars will die, and energy will spread thinner across ever-growing space. But in this middle era, the age of stars and galaxies, we live at a special time. Entropy is rising rapidly, producing structure, light, and life. It is a golden age of cosmic creativity, a fleeting moment in the universe's long journey from order to disorder. We have traced entropy from the astonishing smoothness of the Big Bang through the formation of galaxies, stars, and black holes. But the second law of thermodynamics does not rest. It continues to shape the cosmos not only in the past and present, but also in the vast future that lies ahead. To understand entropy's role in the universe, we must project billions, trillions, and even unimaginable numbers of years into the future. What awaits a universe governed by the relentless rise of entropy? The present era, the age of stars right now. We live in what cosmologists call the stelliferous era, the age of stars. Roughly 13.8 billion years after the Big Bang, stars light the night sky. Galaxies swirl in breathtaking spirals, and planets orbit their suns. Entropy rises steadily, but life and complexity flourish, fueled by the free energy released by stars. This era is temporary. Stars are finite furnaces, burning hydrogen and helium into heavier elements. Already, some stars have exhausted their fuel, collapsing into white dwarfs, neutron stars, or black holes. Others will follow. Over the next trillions of years, the universe will gradually dim as starlight fades. Entropy ensures that this brilliant chapter of cosmic history cannot last forever. The degenerate era. When stars are ganas, stars die out. The universe will enter what physicists call the degenerate era. In this phase, the night sky will be dark. The only objects remaining will be stellar remnants, white dwarfs, neutron stars, and black holes. But even these remnants will not last. White dwarfs will cool slowly, becoming dark. Cold objects, sometimes called black dwarfs. Neutron stars will drift through the darkness, while black holes continue to grow, swallowing stray matter. Entropy in this era is very different from entropy today. Instead of radiant energy spreading across the cosmos, it is the slow fading of heat into near uniformity. The universe will still evolve, but on timescales so vast, they make the age of the current universe seem fleeting. Black hole dominance, entropies, giants. Eventually, black holes will dominate the entropy budget of the cosmos. Remember, black holes are the most entropic objects known. A single supermassive black hole at a galactic center can have more entropy than trillions of stars combined. Over time, galaxies will merge, and their central black holes will collide, growing even larger. The universe will become quieter, colder, and emptier. But entropy will continue to rise through the growth and evaporation of black holes. This leads to one of the most astonishing predictions in modern physics: black hole evaporation. According to Stephen Hawking, black holes are not eternal. They emit a faint radiation, now called Hawking radiation, which slowly causes them to lose mass. For a stellar-sized black hole, this process takes far longer than the current age of the universe. But given enough time, 10,671,067. 1067 years or more, black holes will evaporate, releasing their energy back into the cosmos. This evaporation process represents one of entropy's most dramatic acts: the transformation of massive, dense objects into diffuse radiation spread across space. The dark era entropy's silence. After the last black hole evaporates, the universe will enter what physicists call the dark era. No stars, no galaxies, no light. Only a thin soup of particles, photons, neutrinos, electrons, and positrons drifting in near-perfect equilibrium. Entropy at this point will be almost maximal. The universe will have spread its energy as evenly as possible, leaving no gradients to drive further processes. No stars can ignite, no life can flourish, no complexity can emerge. Time itself will lose meaning because, without change, the concept of time loses its anchor. This state is sometimes referred to as the heat death of the universe. It is not an explosion, nor a fiery end, but a slow fading into silence. A universe where everything that could happen has already happened. Entropy will have reached its ultimate conclusion. Other possibilities: Big Crunch, Big Rip, or cyclic universes. The heat death is the most widely accepted prediction. But physics allows for other possibilities. The Big Crunch, if dark energy behaves differently than we think. The expansion of the universe could eventually reverse, collapsing everything back into a singularity. In this scenario, entropy would rise to unimaginable levels as galaxies, stars, and even atoms are crushed together. The Big Rip, alternatively, if dark energy grows stronger over time, the expansion could accelerate until galaxies, stars, planets, and even atoms are torn apart. Entropy would still rise, but in a violent unraveling of structure. Cyclic universes. Some theories suggest the universe may not end at all, but instead cycle through periods of expansion and collapse. If so, entropy poses a challenge. How can order ever be restored for the next cycle? Does entropy reset, or does each cycle begin with higher disorder than the last? These ideas remain speculative, but they highlight one truth. Entropy is central to any vision of cosmic destiny. Entropy, as cosmic memory, there is a poetic dimension to all of this. Entropy is not just about disorder, it is about history. Each increase in entropy leaves a trace, a memory of what came before. A melted ice cube remembers that it was once frozen. A dying star remembers the billions of years it shone. The expanding universe remembers the entropy dawn of the Big Bang, when entropy finally reaches its maximum. The universe will hold no memory at all. Without gradients, without change, without time, the story ends. In this sense, entropy is both the author and the eraser of the universe's narrative. It writes the tale of galaxies, stars, and life, but it also ensures the book must eventually close. The story of entropy is not confined to the cosmic scale. While the universe's expansion and the rise of galaxies are governed by entropy, the same fundamental law shapes our own planet and everything upon it. Entropy dictates the birth of worlds, the behavior of oceans, the flow of energy, and ultimately, the emergence of life. To understand how deeply entropy permeates our existence, we must begin at the very foundation, the formation of Earth itself. From solar, nebula, to spinning planet around 4.6 billion years ago, our solar system existed as a vast nebula of gas and dust, remnants of earlier generations of stars. This nebula was not uniform. Slight variations in density, influenced by gravity and small perturbations, caused clumps to form. These clumps, through countless collisions and mergers, gradually coalesced into planet symbols, the building blocks of planets. Entropy was central in this process. Initially, the gas and dust represented a relatively low entropy system, particles with specific positions and velocities, slowly drawn together by gravity. Yet, as the particles collided and accreted, kinetic energy transformed into heat, increasing entropy. The chaotic collisions and melting of matter generated energy flows, allowing the young Earth to differentiate into layers, core, mantle, and crust. In this sense, entropy fueled planetary organization, paradoxically creating order out of microscopic chaos. The heat of differentiation, the formation of the Earth's core and mantle, was driven by thermodynamic processes. Dense metals sank toward the center, forming a molten iron core, while lighter silicates rose to form the mantle and crust. As materials moved and melted, heat was released, both from gravitational compression and radioactive decay. This heat, however, did not merely dissipate, drove further entropy increases. Energy radiated into space as the young Earth began to cool, while convection currents within the mantle transported heat, creating the tectonic activity that would shape continents billions of years later. In this process, entropy was the invisible sculptor, channeling energy to forge mountains, oceans, and the planet's magnetic field. Water and the entropy of oceans. One of the most striking aspects of Earth is its oceans. Water is central to life, and its behavior is deeply tied to entropy. When the early Earth cooled enough for water vapor to condense, oceans began to form. Entropy dictated the flow of this water, as energy from the sun drove the hydrological cycle: evaporation, condensation, precipitation, and runoff. This cycle is an elegant example of entropy in action. Solar energy is absorbed by the oceans, breaking hydrogen bonds and allowing water to evaporate into the atmosphere. The water then condenses into clouds and rains back to the surface. In each stage, energy spreads, entropy increases. And yet patterns emerge. Rivers carve valleys, tides shape coastlines, and seasonal cycles regulate ecosystems. Entropy, far from being mere chaos, provides the engine for dynamic order. The role of plate tectonics, another key mechanism for entropy-driven organization, is plate tectonics. The Earth's lithosphere is broken into massive plates that drift atop the viscous mantle. Convection currents in the mantle, fueled by heat from radioactive decay and residual formation energy, push and pull these plates. Collisions produce mountain ranges. Subduction recycles crust into the mantle. From an entropic perspective, tectonics is a process of energy redistribution. The stored energy of the Earth's interior is gradually released, spreading heat outward. Volcanic activity, earthquakes, and mountain building are all manifestations of this energy flow. Each process increases entropy, yet paradoxically gives rise to structure and stability on geological timescales. The continents we live on, the fertile plains we farm, and even the ocean's basins all exist thanks to entropy in motion. Life emerges. Local decrease in entropy as Earth stabilized. Conditions became favorable for the origin of life. This marks one of the most extraordinary entropic paradoxes. Living systems are islands of low entropy, maintaining order by exporting entropy to their surroundings. Energy from the sun, absorbed by Earth, drives chemical reactions that produce increasingly complex molecules. Organic compounds form in primordial oceans, assembling into chains of amino acids and nucleotides. In the process, local order increases as entropy is exported to the surrounding environment, mainly in the form of heat. In essence, life is a mechanism to process energy and entropy simultaneously. Cells take energy, build complex structures, maintain organization, and release waste energy. Without this constant flow of energy and matter, life would collapse into disorder, illustrating the delicate balance between local order and universal entropy. Entropy in early ecosystems. Once life appeared, entropy's influence expanded. Microbial mats, simple colonies, and later multicellular organisms all participate in energy redistribution. Photosynthesis converts solar energy into chemical bonds, storing energy in sugars while releasing oxygen and heat into the environment. Predation, metabolism, reproduction, all these processes are manifestations of entropy at work, constantly redistributing energy and matter. Even the formation of complex ecosystems reflects entropic principles. Energy flows from the sun to plants to herbivores to carnivores, with each step producing waste heat and increasing overall entropy. Ecosystems are dynamic systems far from equilibrium, maintained by continuous energy input. And their order is a temporary structure supported by ongoing entropic processes. The biosphere, entropy at the global scale. A planetary scale, entropy shapes the entire biosphere. Climate systems, ocean currents, wind patterns, and biogeochemical cycles are all driven by energy flows and the redistribution of heat. Life itself contributes, regulating carbon, nitrogen, and water cycles. Entropy does not merely destroy it, drives complexity and sustainability. Without the constant input of solar energy and the redistribution of heat, the Earth's biosphere would stagnate. Life maintains local order by accelerating entropy elsewhere, making our planet a delicate balance of order and disorder as we move from the planetary scale to living systems. The role of entropy becomes even more fascinating. While entropy tends to increase in closed systems, life represents pockets of decreasing entropy maintained by continuous energy flow. Yet these pockets are never isolated. They rely on entropy's inexorable rise in their surroundings. In this way, life is deeply entangled with entropy, both shaping it and being shaped by it. Cellular life order amid disorder at the smallest scale. The cell is a masterclass in managing entropy. Each cell is an organized network of molecules, membranes, and organelles. Proteins fold into precise structures. DNA encodes complex instructions. And energy is carefully distributed via molecules like ATP. This order is maintained by consuming energy, primarily from chemical or solar sources, and releasing waste heat into the environment in thermodynamic terms. Cells decrease their internal entropy while increasing the entropy of their surroundings. They are open systems, exchanging matter and energy continuously. Without this flow, a cell would succumb to disorder and cease functioning. Entropy does not vanish. It is simply exported, demonstrating the subtle interplay between order and chaos. Evolution. Entropy as a creative force. Life does not merely resist entropy. It leverages it. Evolution, driven by variation, selection, and adaptation, can be viewed through the lens of entropy. Mutations introduce randomness, local increases in disorder at the genetic level, but natural selection shapes these variations into complex, functional systems. Paradoxically, the seemingly random processes of mutation and recombination, guided by selection, lead to increasingly sophisticated organisms, ecosystems, and behaviors. Entropy, by introducing variation and energy flow, drives creativity in the biosphere. Life's diversity is not an accident. It emerges because energy, redistribution, and thermodynamic processes create the conditions for complexity. Energy flow in ecosystems. At the ecosystem level, entropy manifests in the flow of energy and matter. Solar energy enters through photosynthesis, fuels primary producers, and cascades through food webs. Each transfer is accompanied by energy loss, heat radiated into the material environment, demonstrating the second law in action. Consider a forest ecosystem. Sunlight energizes leaves, allowing plants to grow. Herbivores consume the plants, carnivores consume the herbivores, and decomposers break down waste and dead organisms. At each step, energy spreads, entropy rises. Yet the ecosystem maintains intricate structures, cycles, and relationships. Entropy creates dynamic order rather than static uniformity. Human systems, entropy at a cultural scale. Humans are also subject to entropy, not just biologically, but socially and technologically. Cities, economies, and technologies all rely on energy to maintain structure. Without constant inputs, food, electricity, labor order collapses into disorder. For example, consider a modern city. Roads, buildings, electrical grids, and communication networks represent highly ordered structures. Maintaining them requires continuous energy flow, power plants, supply chains, and human labor. Over time, entropy infiltrates. Wear and tear, resource depletion, and social decay challenge the system. In response, humans expend energy and ingenuity to preserve order. Even at the level of information, entropy plays a role. Digital systems, libraries, and databases require energy and effort to prevent decay and data loss. Knowledge itself is a form of local order maintained against the universal tide of entropy. The biosphere as an entropic machine viewed globally. The Earth's biosphere is a vast entropic system. Life organizes, energy flows, redistributes matter, and generates local order while increasing entropy at planetary scales. Atmospheric circulation, ocean currents, volcanic activity, and weather patterns all interact with biological systems to maintain dynamic balance. This perspective reveals a profound principle. Life does not violate the second law of thermodynamics, it exploits it. By using energy to maintain structure, generate diversity, and facilitate evolution. Living systems are entropy processors, converting energy into complexity and spreading disorder into their environment. Entropy and extinction. Extinction, yet entropy's influence is also visible in extinction. Every species eventually disappears. Ecosystems collapse, climates shift, and genetic information is lost. These events represent local spikes in disorder, a reminder that no system resists entropy indefinitely. Even human civilization is not immune. Without energy and resources, cities and societies would decay, returning order to disorder. Extinction illustrates a crucial point. Entropy is not evil, it is inevitable. It drives cycles of creation and destruction, shaping life in both subtle and dramatic ways. Without entropy, evolution would stall, ecosystems would stagnate, and complexity would never arise. Entropy, aging, and mortality, a more personal scale. Entropy explains aging and mortality. Biological organisms are constantly fighting molecular disorder, DNA damage, protein misfolding, and cellular degradation increase internal entropy. Metabolic processes help repair and maintain structure, but eventually, entropy wins. Cells die, organs fail, and organisms perish. Aging is not a flaw, it is the natural consequence of thermodynamic law. Life's order is temporary, maintained only by constant energy input and repair mechanisms. This understanding can foster appreciation. Every heartbeat, every thought, every act of life is a temporary triumph over entropy. Entropy's influence stretches beyond biology, shaping human civilization, technology, and even consciousness itself. Understanding this interplay can illuminate why our societies are both resilient and fragile, why technological progress is accompanied by decay, and how life on Earth continues to navigate the delicate balance between order and chaos. Humanity as an entropic agent, humans are remarkable not only for our ability to create order, but also for the scope at which we manage entropy. Cities, infrastructure, transportation networks, and digital systems all require continuous energy input to resist decay. Roads crumble without maintenance, power grids fail without electricity, and information is lost without backups. Yet human activity is not merely defensive against entropy. We actively shape energy flows, redirect matter, and transform environments. Agriculture converts sunlight into calories and organizes vast landscapes. Factories convert raw materials into complex machines. Even art and culture represent a local defiance of entropy, preserving information and experience across generations in thermodynamic terms. Humans are entropy processors on a planetary scale. Every action redistributes energy and matter, increasing entropy globally while maintaining local pockets of order. Our civilization is a microcosm of the broader entropic dance that governs life and the Earth itself. Technology and entropy. Technology is humanity's most sophisticated tool for manipulating entropy. Machines convert energy into work, computers process information, and cities concentrate matter and energy into functional structures. However, technology cannot escape thermodynamic law. Every engine produces heat, every circuit generates waste energy, and every building requires maintenance. Even the digital world is subject to entropy. Data decays, storage media degrade, and hardware fails. The pursuit of sustainability, renewable energy, recycling, and repair can be understood as attempts to locally manage entropy while accepting its unavoidable increase elsewhere. Entropy also drives innovation. The challenges posed by resource limits, decay, and inefficiency stimulate creative solutions. In this sense, entropy is not only a constraint, it is a catalyst for human ingenuity, shaping technological evolution in ways that mirror biological evolution. Consciousness and the mind. Entropy is not limited to matter and energy. It also shapes our minds. The brain is an incredibly ordered system, maintaining precise networks of neurons and chemical gradients. To function, it constantly consumes energy. generating heat and releasing entropy into the body. Memory, thought, and consciousness are manifestations of organized energy flow. Our brains maintain order in the face of thermal noise, molecular decay, and information loss. Yet entropy ensures that forgetting, degradation, and cognitive limitations are inevitable. Every thought is temporary, every memory susceptible to distortion, and every system of knowledge eventually faces decay. Recognizing entropy's role in cognition provides a humbling perspective. Intelligence and consciousness are not exceptions to the second law. They are products of its operation, sustained by energy input and subject to its inexorable march. Entropy in societies and culture societies, like organisms, are open systems. They maintain order through laws, institutions, education, and culture. Yet entropy infiltrates over time. Corruption, social decay, environmental degradation, and conflicts erode stability. Civilizations rise and fall, often due to failures in managing energy and resources efficiently. Historical empires, Roman, Mayan, Ottoman, illustrate how local order can collapse under entropic pressures. Energy scarcity, political mismanagement, and environmental change increase disorder, demonstrating the universality of entropy in human affairs. Even culture itself is entropic. Knowledge and traditions degrade if not actively preserved. Oral histories fade, texts decay, and digital files become obsolete. Yet each generation can resist this trend by creating archives, libraries, and digital backups, highlighting humanity's ongoing struggle to maintain order against entropy, climate, energy, and global entropy, a planetary scale. Entropy governs Earth's climate and energy cycles. The sun provides a constant flow of energy, driving winds, ocean currents, and weather patterns. These systems redistribute energy and matter, increasing entropy globally while allowing life to thrive locally. Human activity, however, accelerates entropic processes. Fossil fuel consumption releases stored solar energy rapidly, altering atmospheric composition and climate. Deforestation and urbanization change energy flow patterns, while pollution spreads disorder through ecosystems. In essence, humanity has become a major agent of entropy, transforming the Earth at unprecedented scales. Understanding this role is crucial. By recognizing the thermodynamic consequences of our actions, we can design systems renewable energy, sustainable agriculture, and circular economies that manage entropy responsibly, maintaining local order while accommodating inevitable global increase. Entropy and the limits of life. Entropy also sets boundaries for life itself. Biological systems can only maintain order temporarily, requiring constant energy input. Starvation, environmental collapse, and disease are manifestations of entropy's influence. Even human longevity is bounded by molecular decay and thermodynamic constraints, yet life's ability to harness energy and maintain structure is astounding. Evolution has optimized organisms to manage entropy efficiently. From photosynthesis to respiration, from neural networks to ecosystems, life transforms energy into order while respecting the second law. This delicate balance is what makes Earth habitable and extraordinary future scenarios. Humanity and entropy. Looking ahead, entropy will continue to shape humanity and Earth. Energy consumption, climate change, technological expansion, and cosmic events all operate within thermodynamic constraints. Our survival depends on adapting to entropy, designing systems that efficiently redistribute energy, recycle matter, and minimize waste. Space exploration also represents a form of entropic management. By harnessing energy from stars, mining resources from asteroids, and colonizing other planets, humanity could maintain local order on scales far beyond Earth. Yet entropy will always remain, reminding us that nothing is permanent and every order is temporary. Entropy as a philosophical lens. Finally, Entropy offers a profound philosophical perspective. It reminds us that all things life, civilizations, planets, and even stars are temporary structures maintained through energy flow. Our achievements, beauty, and consciousness are fleeting, sustained against the universal tide of disorder. Yet this perspective is not discouraging. Understanding entropy enhances appreciation for life's complexity and fragility. Every sunset, every organism, every civilization is a testament to the temporary triumph of order. Entropy frames existence as a dynamic interplay between creation and decay, between structure and chaos, a dance that defines the universe and our place within it. Entropy is not a distant concept reserved for physicists or cosmologists. It permeates every aspect of daily life, from the moment we wake to the time we go to sleep. The second law of thermodynamics quietly governs our surroundings, influencing the flow of energy, the organization of objects, and even the pace at which we age and decay. To truly appreciate entropy, we must first recognize it in the familiar environment of our homes. The kitchen chaos and energy flow. Consider the kitchen, the heart of a home where energy transforms and matter changes form. Cooking is an excellent example of entropy in action. When we boil water, heat energy spreads through the liquid, increasing molecular motion. Ingredients combine, chemical reactions occur, and heat dissipates into the air, while the final meal may appear orderly, neatly arranged on plates. The process of cooking involves enormous energy dispersion. The stove converts electricity or gas into heat, which spreads through the environment, and entropy rises as energy flows from hot to cold regions. Even washing dishes is governed by entropy. Water and detergent help molecules rearrange, food residues disperse, and heat energy leaves the system as entropy increases. Entropy in the kitchen is a daily reminder that order requires effort. Without consistent input, cooking, cleaning, organizing, disorder accumulates. Dirty dishes pile up, ingredients spoil, and the once tidy environment becomes chaotic. This mirrors cosmic and biological processes. Maintaining order always requires energy expenditure. Household maintenance, fighting, homes themselves are battlegrounds against entropy. Floors gather dust, walls discolor, appliances break down, and furniture wears. These are natural consequences of the second law. Every material, from wood to metal to fabric, is subject to gradual decay, reflecting the slow but inevitable increase in disorder. Maintaining a household requires constant energy input. Vacuuming, painting, repairing, and replacing parts are ways of locally decreasing entropy at the cost of energy and resources. Left unchecked, entropy dominates. Structures weaken, mechanical systems fail, and chaos emerges. In this sense, housekeeping is a microcosm of life's broader entropic challenge. Every bit of order we maintain consumes energy and effort, clothing and personal care, small-scale entropy. Even personal routines reflect entropic principles. Clothes wrinkle, shoes wear, and hair grows messy, all manifestations of disorder increasing in local systems. Washing, ironing, trimming, and grooming are energy-intensive ways humans manage local entropy. Consider a closet without regular attention. Clothes tangle, dust accumulates, and the environment descends into disarray. Each small act of organization, folding shirts, hanging coats, polishing shoes, is a localized reversal of entropy, sustained temporarily by energy expenditure. Entropy ensures that order is fleeting, emphasizing that every system, no matter how small, tends toward disorder unless actively managed. Refrigeration slowing. Entropy locally refrigerators provide an excellent example of controlling entropy. By consuming electrical energy, they maintain a low-temperature environment that slows molecular motion, delaying food spoilage. However, the process itself increases entropy in the wider system. The fridge's compressor releases heat into the room. The electricity powering it comes from energy generation, often fossil fuels, and waste heat is dispersed. In thermodynamic terms, we do not violate the second law. We simply transfer entropy elsewhere to maintain temporary order in our food. This principle extends to nearly every technological convenience in daily life. Daily. Objects and tools. The invisible march of entropy. Every object we use is subject to decay. Phones slow down, batteries degrade, furniture scratches, and buildings erode. These changes reflect the gradual dispersion of energy and the inevitable rise of entropy. Humans attempt to counteract this decay through repairs, upgrades, and replacements. Software updates, protective coatings, cleaning products, and mechanical maintenance are all methods of pushing back against entropy locally, recognizing that without intervention, disorder will dominate. Personal energy, biological entropy. Entropy also governs our bodies. Cells metabolize food to produce energy, which powers every action we take. As we age, entropy manifests in molecular damage, protein misfolding, and cellular decay. Sleep, exercise, nutrition, and medicine are ways we attempt to manage biological entropy, slowing the progression of disorder within our own systems. Even mental processes obey entropic rules. Learning, memory, and cognition require constant energy input, attention, and repetition to maintain order in neural networks. Forgetting and mental fatigue reflect the natural tendency toward increasing disorder. Daily routines. A dance with disorder, from the mundane act of making the bed to the complex organization of a workday. Human routines are strategies to manage entropy continuously. Without these routines, disorder spreads, tasks pile up, objects scatter, and time feels chaotic. Entropy reminds us that stability is never permanent. It must be actively maintained. Understanding this daily struggle offers a profound perspective. Even small acts of organization are victories against universal laws. Every cup washed, every desk organized, every email answered is part of a broader entropic process, a microcosm of the universe's tendency toward disorder. Entropy is not just a physical LUT, deeply influences human behavior, social interactions, and the way we organize our work and communities. While we often perceive daily life as orderly and purposeful, the underlying tendency toward disorder subtly shapes our decisions, productivity, and relationships. Understanding entropy in this context offers insights into human efficiency, cooperation, and even creativity. Productivity and the battle against disorder. Every day, individuals manage numerous tasks, emails, meetings, household chores, and personal responsibilities. Without structure, these tasks quickly become chaotic, piling up and overwhelming the mind. Entropy explains why clutter, procrastination, and inefficiency naturally emerge. Time, like energy, is a finite resource. As we distribute attention across multiple tasks, disorder in our personal systems increases. For instance, an overflowing inbox is a physical manifestation of entropic accumulation. Information spreads unchecked. Organization decays, and important messages are lost. Productivity tools, calendars, task lists, reminders serve as entropy management systems. They help redistribute mental and physical energy, creating temporary pockets of order. However, these systems require constant input. Neglect leads to disorder, illustrating the universality of entropy at the level of personal organization, habits, and routine. Entropy management and action habits are an elegant human adaptation to entropy. By automating repetitive behaviors, we conserve energy and maintain local order without constant conscious effort. Brushing teeth, making the bed, or following a morning routine reduces cognitive load, preventing the mental chaos that arises from entropy's natural influence. Interestingly, entropy also encourages innovation. Small amounts of randomness or disruption in routines can lead to creative solutions. When a habitual pattern is broken, The resulting disorder often prompts new strategies, new insights, or unexpected connections. In this sense, entropy is both a challenge and a driver of growth, shaping behavior in subtle, productive ways. Social systems, entropy in human networks communities. Organizations and societies are large-scale entropic systems. Relationships, rules, and institutions represent structured order maintained through energy, effort, and attention. However, entropy infiltrates constantly. Conflicts arise. Resources are misallocated and information becomes distorted. Consider a workplace. Teams operate under shared rules and processes, yet inefficiencies, miscommunication, procrastination, or poorly defined roles gradually increase disorder. Managers, policies, and systems act as entropy-controlling mechanisms, redistributing energy to maintain order. The balance between structured organization and the natural drift toward chaos mirrors thermodynamic principles. Entropy is inevitable, but localized order is achievable through consistent effort. Entropy in communication language. Information sharing and memory are deeply entropic processes. Every conversation introduces noise and distortion. Messages are misunderstood, details are forgotten, and information disperses. Texts, emails, and social media amplify this effect, spreading data widely and increasing informational entropy. Humans combat this through repetition, documentation, and clarification. Meetings, reports, and recordings are tools to reduce disorder locally. Yet, even these systems are temporary. Information decays, systems fail, and entropy reasserts itself. Effective communication is, at its core, a thermodynamic battle against disorder, constantly requiring energy and attention. Decision-making and entropic decision-making is another domain where entropy manifests. The more options, variables, and uncertainties we face, the higher the potential for disorder in outcomes. Without careful analysis, randomness and inefficiency dominate, reflecting the natural tendency toward increasing entropy. Structured frameworks, pros and cons lists. Algorithms or statistical models help manage this uncertainty. They channel mental energy to reduce disorder and improve outcomes. Yet even the most sophisticated planning cannot eliminate entropy entirely. Unforeseen events, imperfect knowledge, and human error always introduce unpredictability. Creativity and entropy, order from chaos paradoxically. Entropy also fosters creativity. Randomness, disorder, and unexpected connections stimulate innovation, artistic expression, and scientific discovery. Writers, musicians, and inventors often harness disorder, experimenting with ideas until patterns emerge. Entropy provides the raw material for novelty. Without disorder, there would be no divergence, no chance to recombine ideas, and no impetus for growth. Creative processes exemplify the interplay between chaos and order. The mind explores possibilities. Energy flows through neural networks, and eventually structured results paintings, compositions, inventions emerge. Leisure, play, and entropy. Even leisure activities demonstrate entropic principles. Games, sports, and hobbies often involve navigating random challenges, balancing structure with unpredictability. Sports, for example, rely on rules to impose order, yet the outcome is inherently uncertain. Players adapt strategies dynamically, responding to fluctuations in the system. Entropy ensures that no system remains static. The playful chaos of human interactions, games, and spontaneous events illustrates how disorder creates opportunities for engagement, learning, and social bonding. Without entropy, human experience would be rigid, predictable, and uninspired. Health and energy management. Our bodies are constant arenas of entropic activity. Metabolism transforms food into energy, powering muscles, organs, and the brain. Aging, injury, and disease represent natural increases in disorder at the molecular and systemic levels. We combat these entropic effects through diet, exercise, sleep, and medical interventions. Even mental practices, mindfulness, meditation, and focused work help maintain cognitive order amidst the brain's natural tendency toward chaos. Every effort to preserve health is fundamentally a fight against entropy. Asterisk. Entropy not only shapes personal life and behavior, but also governs the larger systems humans have built: technology, cities, and societies. Understanding how disorder naturally arises in these domains provides insight into both their fragility and resilience, as well as our role in maintaining them. Technology order at a cost. Modern technology is a remarkable when to work. Remarkable achievement of human ingenuity. Yet it operates under the unyielding rules of thermodynamics. Every device, from smartphones to skyscrapers, requires energy to maintain its functionality and resist decay. Computers need electricity to operate. Servers need cooling systems to prevent overheating. Even software requires updates and debugging to maintain order. At the same time, every action generates entropy. Heat dissipates, materials wear, and circuits degrade. For instance, data centers consume massive amounts of energy, not just to process information, but also to counteract entropy by cooling equipment and replacing failing hardware. Even our digital lives are entropic. Files become corrupted, devices crash, and networks experience delays or failures. Efforts to back up, update, and repair represent localized reductions of entropy, while the broader universe continues its inexorable increase in disorder. Cities as entropic systems. Urban life provides a tangible example of entropy on a massive scale. Cities concentrate humans, infrastructure, and energy into complex, organized systems. Streets, electricity grids, water networks, and transportation systems all function as ordered structures that fight disorder. Yet, cities are constantly under entropic pressure. Traffic congestion, power outages, pollution, and social unrest are manifestations of disorder infiltrating highly organized systems. Infrastructure requires continuous maintenance, from repairing roads to replacing water pipes and stabilizing buildings. Without constant energy and labor input, cities would quickly decay into chaos. Interestingly, entropy also drives urban innovation. Challenges such as congestion or resource scarcity force humans to develop creative solutions: public transit systems, energy-efficient buildings, and digital planning tools, demonstrating that disorder can be a catalyst for progress. Societal systems, order amid complexity beyond cities. Entire societies are subject to entropic forces. Governance, economies, legal systems, and cultural norms represent ordered structures that require constant energy, attention, and adaptation. Without active management, social disorder can increase rapidly. Political instability, economic crises, and social conflicts all reflect rising entropy. Education and cultural preservation are human strategies to manage social entropy. Knowledge, values, and skills must be continually transmitted and reinforced to maintain order. Libraries, schools, and digital archives are attempts to preserve information against decay. While laws and institutions impose structure to guide collective behavior, yet entropy ensures that no system remains static. Revolutions, technological disruptions, pandemics, and environmental crises demonstrate that disorder can suddenly surge, reshaping societies and forcing adaptation. In this sense, entropy acts as both a constraint and a creative force, driving evolution not only in biology, but also in culture and technology. Energy, consumption, and sustainability, major theme in daily life and societal systems, is the management of energy. Entropy manifests as energy dispersal, resource depletion, and waste generation. Every industrial process, transportation system, and building consumes energy and produces waste heat. Sustainable design, renewable energy, and recycling efforts are responses to entropic pressure. They attempt to optimize energy use and slow the accumulation of disorder, creating more efficient systems while recognizing that entropy cannot be eliminated. This balance between order and energy efficiency defines modern approaches to environmental management and urban planning. Transportation and entropy transportation systems are microcosms of entropic principles. Roads, railways, airports, and shipping networks concentrate order and require continuous energy to maintain. Vehicles consume fuel, engines produce heat, and mechanical parts wear over time. Traffic congestion, accidents, and infrastructure failure illustrate entropy at work. As disorder naturally infiltrates even the most meticulously planned systems, human responses maintenance, traffic control, and logistics planning are localized efforts to maintain order. Even innovation in autonomous vehicles, traffic algorithms, and high-speed rail is motivated by the need to control entropic pressures, making movement more efficient and predictable. Information systems, digital entropy, digital life is particularly entropic. Information spreads rapidly, degrades over time, and becomes obsolete. Social media amplifies this effect, dispersing data widely and increasing informational entropy. Cybersecurity threats, hardware failure, and software bugs all contribute to disorder. Efforts to manage digital entropy backups, encryption, updates, and server maintenance mirror physical world strategies for maintaining order. Even as data grows exponentially, localized systems of organization allow humans to temporarily resist chaos, preserving knowledge, connections, and functionality. Entropy and global society, the planetary scale. Humanity's influence on entropy is immense. Industrialization, deforestation, and climate change accelerate disorder in natural systems. Resource depletion, species extinction, and pollution represent rising entropy across ecosystems. Yet this same entropic pressure can drive solutions. Renewable energy, sustainable agriculture, and conservation initiatives are examples of humans using energy to locally reduce disorder, creating balance amid global complexity. Recognizing the thermodynamic constraints on human activity encourages innovation, cooperation, and long-term planning. Entropy is intimately linked to time. In physics, the arrow of time is defined by the direction in which entropy increases. This fundamental relationship means that as time progresses, disorder in the universe tends to rise, shaping everything from the decay of stars to the ultimate fate of galaxies. Understanding entropy in this cosmic context gives us a profound glimpse into the universe's long-term trajectory and the inevitability of its changes. Entropy as the arrow of time and entropy are inseparable. In a closed system, entropy increases monotonically, and this increase defines the direction of time. While fundamental physical laws are mostly time-symmetric, entropy gives time its asymmetry. We remember the past, but not the future. Eggs break, but do not spontaneously reassemble. And stars burn fuel, but do not reverse their nuclear reactions. This principle explains why the universe appears to evolve in one direction. From the Big Bang onward, entropy has been rising steadily. Matter organizes locally forming stars, planets, and life, but globally, the total disorder increases. Time, as we perceive it, is the story of this entropic progression. Heat death and cosmic fate. One of the most discussed consequences of entropy is the concept of heat death. If the universe continues to expand indefinitely, energy will spread ever more thinly. Stars will burn out, galaxies will drift apart, and temperatures will approach uniformity. In this state, no work can be extracted from energy differences. All processes cease, and the universe reaches maximum entropy. Heat death is not an abrupt event, but a gradual process. First, stars exhaust their nuclear fuel. Planets cool, black holes slowly evaporate through Hawking radiation, and galaxies fade into darkness. Finally, after trillions of years, the universe reaches a state of thermodynamic equilibrium, where all structure and life as we know it becomes impossible. This scenario underscores the ultimate power of entropy, even the grandest structures of matter. Energy and information are temporary arrangements, maintained only by energy flows that are finite and depleting. Entropy and the fate of life is a local exception to the universal trend of disorder sustained by energy from stars and other sources. Yet even life is bounded by entropy. Biological systems consume energy to maintain order, but resources are finite. In the very long term, the same thermodynamic rules that govern stars and planets will limit life's persistence. Consider the far future. As stars fade and energy gradients diminish, sustaining life becomes increasingly difficult. Any civilizations that survive must adapt to increasingly entropic conditions, potentially relying on advanced technology, energy storage, or cosmic engineering to maintain order. Entropy places hard constraints on longevity and civilization, emphasizing that even the most advanced life forms are ultimately bound by physical law. Black holes and entropy. Black holes represent some of the most extreme examples of entropy in the universe. According to physicist Stephen Hawking, black holes are the densest forms of disorder possible, with entropy proportional to the area of their event horizons. They absorb matter and energy, hiding information from the outside world and contributing to the universe's overall entropic growth. Hawking, radiation suggests that black holes slowly evaporate over time, releasing energy back into the universe and increasing entropy elsewhere. Even these seemingly eternal structures are subject to entropic decay, demonstrating the universality of the second law. Black holes illustrate how entropy governs not only ordinary matter, but also the most exotic objects in the cosmos. Time, memory, and cosmic perspective. Entropy also shapes our perception of time. Human memory relies on ordered structures in the brain, which are maintained locally while increasing overall entropy in the body and environment. Our experience of the flow of time is essentially an entropic experience. We remember the past lower entropy states, but cannot perceive the future higher entropy states yet to unfold. Cosmologically, this perspective highlights the inevitability of change. Galaxies collide, stars die, and black holes evaporate. The universe itself is a record of rising entropy, a vast chronicle of transformation where every moment is both a creation of order and a contribution to disorder. The ultimate temporal horizon, entropy, defines the ultimate horizon of time. No matter how advanced civilizations become, no matter how effectively energy is harnessed, the long-term future of the universe is governed by the increase of disorder. This horizon is not merely theoretical. It is the logical conclusion of thermodynamics applied on a cosmic scale. Future scenarios, heat death, the Big Freeze, or even potential quantum fluctuations in a cold, high-entropy universe underscore the inexorability of entropy. Time, energy, and matter are inseparable from this process. And the story of the universe is the story of disorder increasing relentlessly. Entropy is a universal principle that governs not only the large-scale structure of the cosmos, but also the tiniest quantum systems. From the behavior of galaxies to the probabilistic rules of subatomic particles, entropy shapes the evolution of the universe in ways both subtle and dramatic. Understanding these connections allows us to glimpse how disorder operates across scales from the infinitesimal to the cosmic. Cosmic expansion and entropy. The universe is expanding, and this expansion directly affects entropy. As space stretches, energy becomes more diffuse, and the temperature of radiation falls. The cosmic microwave background, the afterglow of the Big Bang, is gradually cooling, representing a steady increase in entropy as energy spreads over an ever larger volume. Stars and galaxies, represent temporary reductions in entropy, where matter clumps together under gravity. These pockets of order persist only because the surrounding universe is vast and disordered. Over billions of years, as stars exhaust their fuel and galaxies drift apart, localized order diminishes and entropy rises globally. The expansion of the universe is, therefore, both a driver and a consequence of entropic increase, illustrating the deep connection between cosmology and thermodynamics. Black holes. Entropy extremes. Black holes are perhaps the most fascinating examples of cosmic entropy. Their event horizons hide enormous amounts of information, and the entropy of a black hole is proportional to the surface area of its boundary. Unlike ordinary matter, which disperses gradually, black holes concentrate disorder in an incredibly dense form. Stephen Hawking's prediction of black hole evaporation demonstrates that even these extreme systems are subject to entropy's inexorable rise. As they radiate energy over trillions of years, information is released in highly scrambled forms, contributing to universal disorder. Black holes are cosmic reminders that no structure, no matter how extreme, escapes entropy. Quantum systems and probabilistic entropy also governs the microscopic world. Quantum systems, governed by probabilities rather than certainties, reflect the same tendency toward disorder. In quantum mechanics, particles exist in superpositions, multiple potential states until observed. The act of measurement collapses these possibilities into a specific outcome. Yet over time, the probabilities disperse, creating a natural increase in entropy. Even at the smallest scales, disorder is fundamental. The unpredictability of quantum states, the scattering of particles, and the statistical nature of thermodynamic systems all demonstrate that. Entropy is not merely a macroscopic phenomenon. It is woven into the very fabric of reality. The heat-death revisited connecting. Cosmic and quantum entropy leads us to the ultimate fate of the universe. Heat death, or the Big Freeze, is the state of maximum entropy, where energy is uniform and no work can be performed. Stars die, black holes evaporate, and even quantum fluctuations lose their ability to create organized structures. At this point, time continues, but all meaningful change ceases. The universe becomes a vast, cold, uniform expanse where disorder dominates completely. Every structure, from atoms to galaxies, has been reduced to its simplest, most entropic state. Heat death is not catastrophic in the traditional sense, is the inevitable thermodynamic equilibrium toward which the universe steadily moves. Entropy, and the arrow of time entropy, defines the arrow of time, the direction in which events unfold. While the fundamental laws of physics are mostly symmetric with respect to time, entropy breaks this symmetry. We remember the past, but not the future. Ice melts, but does not spontaneously refreeze. Stars burn fuel, but do not reverse nuclear fusion. This one-way flow of time underlines the connection between entropy and cosmological evolution. The universe's expansion, star formation, planetary development, and eventual decay all occur in the direction dictated by increasing disorder. Understanding this arrow provides not only a framework for physics, but also a philosophical lens for understanding impermanence, causality, and the passage of time itself. Life and complexity in a universe of increasing entropy, in a universe tending toward disorder. Complexity can emerge locally. Life, civilizations, technology, and knowledge all represent temporary reductions of entropy. By consuming energy, organisms create order in their immediate environment, maintaining intricate structures and processes that resist decay. However, this local reduction comes at a cost. Energy used to create order inevitably increases entropy elsewhere. The rise and fall of civilizations, the growth and decay of ecosystems, and the evolution of species all occur within this framework. Life is essentially a localized battle against universal disorder, vibrant but temporary, constantly fueled by energy from stars and other sources. Cosmic perspective. Small islands of order from a cosmic perspective. Humanity is an island of order in an ocean of increasing entropy. Our technology, cities, culture, and knowledge temporarily slow disorder in localized pockets. Yet the universe as a whole continues its inexorable journey toward thermodynamic equilibrium. Even the most advanced civilizations must contend with entropy. Energy sources are finite, structures decay, and over trillions of years, all ordered systems succumb. Recognizing this universal law encourages both humility and wonder. Every act of creation, every scientific discovery, and every moment of life represents a triumph against an inevitable tie to temporary arrangement of matter and energy in a universe that favors disorder. As we've explored, entropy drives the universe toward increasing disorder, ultimately determining its fate. While the concept may seem abstract or distant, it shapes everything from the behavior of matter to the longevity of life and civilizations. In this final part of Chapter 5, we will explore the ultimate consequences of entropy and the speculative possibilities for the universe's distant future. The inevitable end: the universe is not immortal. Stars burn through their nuclear fuel, planets cool, and galaxies drift apart. Black holes slowly evaporate via Hawking radiation. Eventually, the cosmos reaches maximum entropy, a state in which all energy is evenly distributed and no work can be done. This is the thermodynamic end, sometimes called the heat death of the universe. At this point, time continues, but change as we know it ceases. There are no gradients of energy to drive chemical reactions, biological processes, or technological activity. Even quantum fluctuations become rare, and the universe becomes a vast cold and dark expanse, a place where disorder reigns supreme. Entropy, in this sense, is the ultimate arbiter of time, governing the beginning, the middle, and the end of cosmic history. The universe's evolution is not chaotic, but follows a predictable entropic trajectory, where every system gradually contributes to the overall increase in disorder. Speculative scenarios for the distant future. Physicists and cosmologists have proposed several possible scenarios for the universe's far future, all shaped by entropy. One scenario is the Big Freeze, in which expansion continues forever. Stars burn out, and entropy reaches a maximum. Another is the Big Rip, where the expansion accelerates so rapidly that galaxies, stars, planets, and eventually atoms are torn apart. Quantum mechanics adds layers of uncertainty and possibility, even in a universe tending toward maximum entropy. Rare fluctuations could create temporary pockets of low entropy, potentially forming new structures, stars, or even universes. These quantum islands would be fleeting, yet they illustrate the unpredictable creativity that arises even in a predominantly disordered cosmos. Life in an entropic universe. Life is a temporary reprieve from universal disorder. Organisms, civilizations, and technological systems consume energy to maintain order locally, but this comes at the cost of increasing entropy elsewhere. Eventually, energy gradients become insufficient to sustain life, and biological processes halt advanced civilizations. If they endure for billions or trillions of years, might attempt extraordinary measures, storing energy, controlling black holes, or engineering entire star systems. Yet even these measures are ultimately limited. Entropy ensures that no matter how advanced, the universe will gradually approach uniformity, and all organized systems will succumb. Entropy and the philosophy of time. Entropy is more than a physical lit, is a lens through which we can interpret existence. The arrow of time, memory, causality, and change are all consequences of increasing disorder. From a philosophical perspective, entropy highlights the impermanence of all things. encouraging a deeper appreciation for transient moments of order and life itself. Human experience, creativity, and achievement are meaningful precisely because they exist against the backdrop of inevitable decay. Understanding entropy gives context to our endeavors. Every act of creation, every innovation, and every moment of beauty is a temporary triumph in a universe that favors disorder. Cosmic engineering and speculative futures, some speculative. Thinkers have imagined ways to delay or manage entropy on cosmic scales. Dyson spheres, advanced energy storage, or controlled manipulation of black holes might extend the lifetime of civilizations, even in a universe tending toward maximum disorder. Localized pockets of order could persist for extraordinary lengths of time. However, these interventions are temporary solutions. While they can slow the increase of entropy locally, they cannot reverse the fundamental trend. The universe, on the grand scale, is inexorably moving toward uniformity, and entropy remains the ultimate determinant of cosmic destiny. The beauty of temporary order, recognizing the inevitability of entropy, does not diminish the wonder of existence. On the contrary, it highlights the significance of every moment of order, every act of life, and every structure maintained against disorder. Stars shine briefly, civilizations flourish temporarily, and life persists against the odds, all because energy flows. Allow local reductions in entropy. Entropy teaches humility and awe. It reminds us that even the grandest accomplishments are transient and that beauty and structure are remarkable, precisely because they exist against a universal tide of disorder. This perspective can deepen our appreciation for both the cosmos and our own fleeting lives. Entropy is not only a measure of disorder in physical systems, it also governs information. In the mid-20th century, Claude Shannon formalized the concept of information entropy, quantifying uncertainty in data and communication. Information, like energy, is subject to the universal tendencies of disorder. Understanding this relationship offers profound insight into how knowledge, chaos, and order interconnect in the universe. Information as a physical quantity, while information is often thought of as abstract, it has a physical foundation. Every message, memory, or data file exists in a medium: paper, neurons, magnetic storage, or electronic circuits. The maintenance of this medium requires energy, and without constant input, information decays. Pages yellow, memories fade, digital files become corrupted. Entropy quantifies this degradation. High information systems have low entropy because the state of the system is highly ordered and predictable. As disorder increases, uncertainty rises, and information is effectively lost. This principle links the physical and informational realms. Entropy governs both energy and knowledge. Shannon entropy, measuring uncertainty. Claude Shannon introduced a mathematical framework to quantify information. Shannon entropy measures the average uncertainty in a set of messages, providing a metric for disorder in communication systems. The more unpredictable a message, the higher its entropy. Conversely, highly structured, predictable messages have lower entropy. This framework allows us to connect physical entropy to information. A closed system tends toward disorder physically, and the information about its precise state becomes increasingly uncertain. In essence, as thermodynamic entropy increases, so does informational entropy. The uncertainty about the system grows. Chaos, complexity, and predictability. Chaos theory explores systems that are deterministic yet highly sensitive to initial conditions. Small variations in starting parameters lead to vastly different outcomes, exemplifying how order can coexist with unpredictability. Entropy measures the inherent disorder in these systems, providing a way to quantify complexity and uncertainty. Weather, ecosystems, and financial markets are real-world examples. While rules govern these systems, small perturbations amplify over time, creating outcomes that are practically unpredictable. Entropy ensures that no system remains perfectly ordered or entirely predictable. Linking chaos to the universal rise of disorder, data, computation, and entropy information processing is also entropic. Computers consume energy to organize bits, execute instructions, and maintain memory states. Each computation increases local order, but produces heat and dissipates energy into the environment, increasing overall entropy. In this sense, computation is a localized battle against disorder. Complex algorithms, artificial intelligence, and data centers function as temporary islands of order, maintaining structure in a world that naturally trends toward chaos. Energy expenditure is essential. Without it, digital information degrades and computation ceases. Entropy in biological information. Entropy also governs life at the molecular level. DNA, the blueprint of living organisms, stores immense quantities of information in highly ordered sequences. Transcription, replication, and repair processes maintain this information against the natural tendency toward disorder. Mutations, errors in replication and cellular damage represent the unavoidable increase of entropy in biological systems. Organisms expend energy through metabolism to maintain information integrity. Life itself is a constant struggle to preserve informational order amidst inevitable chaos. Memory, cognition, and disorder. Human consciousness and memory are profoundly entropic systems. Memories encode information through networks of neurons, creating structured patterns of synaptic connections. However, these networks are dynamic, subject to decay, interference, and noise. Forgetting, misremembering, or confusion represents the manifestation of entropic processes in the mind. Conscious thought navigates this landscape of uncertainty, organizing information, detecting patterns, and predicting outcomes. In doing so, the brain constantly battles entropy locally, using energy to maintain mental order while the overall system remains entropic. Chaos as a source of creativity. Interestingly, entropy and chaos are not purely destructive. They also fuel creativity and innovation. Randomness, disorder, and unpredictability provide the raw material for novelty. Writers, artists, scientists, and engineers often harness disorder, generating ideas and solutions by exploring the space of possibilities that chaos creates. Entropy ensures that no two ideas, moments, or processes are ever identical. While this unpredictability introduces uncertainty, it also enables adaptation, evolution, and growth. Creativity is thus a localized reduction of informational entropy, extracting order from chaos to generate meaningful structure. Entropy not only shapes physical systems and biological life, but also profoundly influences human societies, technology, and the flow of knowledge. Information in social, technological, and cultural networks exists in a dynamic interplay between order and disorder. Understanding how entropy operates at these scales illuminates patterns of stability, disruption, and innovation. Societies as information systems. Human societies are, at their core, complex information systems. Laws, traditions, governance structures, and cultural norms organize individuals into functional networks, reducing social entropy locally. Institutions codify knowledge, transmit it across generations, and create predictability in human behavior. Yet entropy is always present. Societies experience decay, corruption, and disorder. Legal systems falter, cultural knowledge is lost, and social unrest emerges. These are not failures in isolation. They are manifestations of entropy infiltrating large complex systems. Social stability requires constant energy and effort. Education, governance, communication, and cultural reinforcement are all mechanisms to maintain order in the face of disorder, technology, and the battle against disorder. Modern technology represents one of humanity's most ambitious attempts to resist entropy. From digital networks to mechanical infrastructure, technological systems require energy, maintenance, and redundancy to maintain order. Servers must be cooled, software updated, and machinery repaired, all to prevent the inevitable rise of disorder. Computational systems illustrate this concept vividly. Information stored in memory chips or hard drives is subject to physical decay, electromagnetic interference, and hardware failure. Data corruption, system crashes, and cyber threats are entropic forces at work. Engineers counteract these by implementing backups, error correction codes, and secure networks. Each act of maintenance is a localized reduction of entropy, temporarily preserving order in a chaotic environment. Knowledge transmission and informational decay, whether scientific, cultural, or personal, exists in a fragile balance. Books, digital media, and oral traditions store information, but they are not immune to disorder. Pages decay, hard drives fail, and memories fade. Entropy ensures that without active intervention, knowledge disperses and uncertainty grows. Efforts to catalog, digitize, and preserve information reflect humanity's understanding of entropic risk. Libraries, databases, and archival systems are constructed to resist decay. Even artificial intelligence and machine learning attempt to organize chaotic data into meaningful patterns. Mitigating informational entropy. Yet complete prevention is impossible. Disorder is an inherent feature of all complex systems. Chaos as a driver of innovation, while entropy introduces disorder. It also drives novelty and innovation. Randomness and unpredictability create the conditions for creative problem solving. In technological development, unforeseen errors often lead to breakthroughs. In societies, crises catalyze adaptation, reform, and evolution. For example, economic fluctuations, natural disasters, and political upheavals, though disruptive, force societies to reorganize and improve resilience. In the same way, experimental failures in science or engineering reveal unanticipated solutions. Entropy, therefore, is both a challenge and a source of opportunity, fueling complexity and progress. Digital systems and informational entropy. Modern digital era magnifies the interplay between order and disorder. Social media, cloud computing, and global networks disseminate information at unprecedented speeds, but also amplify errors, misinformation, and noise. Digital entropy manifests as data corruption, signal loss, and algorithmic unpredictability. Efforts to organize information search engines, data analytics, and machine learning are strategies to create temporary islands of order. Yet, even as these systems process and structure vast amounts of data, they generate heat and consume energy, increasing physical entropy. The digital world mirrors physical reality. Maintaining order requires continuous input, and disorder is never eliminated. Entropy is not only a force acting on matter, energy, and societies, it also shapes consciousness and the limits of knowledge itself. Our ability to perceive, understand, and organize information is deeply tied to the entropic tendencies of the universe. Every thought, memory, and insight exists as a delicate balance between order and disorder. Consciousness as an entropic system. Human brain is a highly ordered structure, yet it operates in a fundamentally entropic environment. Neurons fire probabilistically, synaptic connections fluctuate, and chemical gradients drive cognition. Maintaining mental order, memory, reasoning, and awareness requires a constant expenditure of energy. Sleep, nutrition, and metabolic processes are necessary. To counteract the natural drift toward disorder, consciousness emerges from this complex interplay. It is both fragile and resilient. Fragile because it can be disrupted by small biochemical or physical changes, yet resilient because it can self-organize, adapt, and recover. In essence, consciousness is a temporary reduction of entropy in a system otherwise governed by disorder. Memory and informational decay illustrates entropy's impact on knowledge at an intimate scale. Every recollection is subject to distortion and loss over time. Forgetting is not merely a psychological phenomenon, it is a manifestation of increasing disorder in neural systems. Synaptic decay, noise, and interference all contribute to informational entropy, making precise memory impossible over long periods. Yet this entropic nature of memory has adaptive benefits. By allowing minor distortions, the brain can prioritize essential information, detect patterns, and respond to a complex, unpredictable environment. Entropy is both a challenge and a mechanism for cognitive efficiency, shaping how humans process and retain knowledge. Limits and the universe. Entropy also imposes fundamental limits on the knowledge we can obtain about the universe. In thermodynamics, uncertainty is inevitable. In quantum mechanics, Heisenberg's principle places bounds on simultaneously knowing certain properties. Entropy ensures that some information is always hidden, inaccessible, or irretrievably lost. These limitations are not merely practical, they are inherent. Black holes hide information behind event horizons, and chaotic systems amplify uncertainty. Even the most sophisticated measurements or simulations encounter entropic barriers. As a result, complete knowledge of any system, physical, biological, or social, is fundamentally unattainable. Creativity, insight, and entropy. Despite these limits, entropy can foster creativity and insight. The unpredictability of disorder creates opportunities for novel connections, ideas, and problem solving. Random fluctuations, errors, and uncertainties can reveal patterns that structured order alone could not. Artists, scientists, and innovators often leverage entropic processes, whether consciously or not. Serendipitous discoveries, unexpected inspirations, and adaptive learning all emerge from the chaotic, entropic dynamics of the world. In this sense, entropy is both a boundary and a source of possibility, shaping the limits and potentials of human knowledge. Conscious decision-making and disordered decision-making is another domain influenced by entropy. Humans make choices under uncertainty, navigating incomplete or conflicting information. The rising disorder in cognitive and informational systems forces prioritization, heuristics, and judgment. Entropy ensures that no plan, no prediction, and no strategy is perfectly secure. Even well-informed decisions are subject to unexpected outcomes, whether due to quantum randomness, environmental fluctuations, or social complexity. The ability to adapt to this uncertainty rather than resist, it is a hallmark of intelligence and resilience. The interplay of order and chaos across all scales. Consciousness exists at the intersection of order and disorder. Neural networks, thought processes, societies, and cultures all rely on structured organization within an entropic environment. This interplay allows the emergence of intelligence, creativity, and self-awareness. Entropy reminds us that all structures are temporary and knowledge is provisional. Yet the very presence of order amidst disorder, conscious thought, life, and civilization is remarkable. It demonstrates how localized reductions of entropy can create profound complexity, awareness, and meaning. The fragility and power of knowledge. Lady. Entropy shapes the fragility and power of knowledge. Every insight, memory, and discovery exists in a context of uncertainty, decay, and transformation. Knowledge is not absolute. It is a living, dynamic system constantly contending with disorder. This perspective can be humbling. It reminds us that every system of thought, every scientific model, and every cultural framework is a temporary triumph over chaos. At the same time, it is empowering. Humans can recognize, understand, and navigate entropic processes, creating order, meaning, and innovation in the face of inevitable uncertainty. Entropy is not only a cosmic or microscopic phenomenon profoundly shapes the existence of humanity. As conscious, intelligent beings, we are unique, localized reductions of entropy, creating order from disorder in a universe that naturally trends toward chaos. Understanding this dynamic illuminates both the fragility and the resilience of human civilization. Humanity in the context of universal disorder from the perspective of the cosmos. Humanity is a fleeting arrangement of matter and energy. Stars burn, planets orbit, and galaxies drift apart, all according to predictable entropic laws. Within this vast entropic universe, human beings have organized themselves into civilizations, societies, and cultures, temporary islands of order maintained through energy, communication, and knowledge. This localized order is remarkable precisely because it exists in opposition to the surrounding chaos. Our city's infrastructure, technology, and social structures all require constant maintenance. Without continuous input, food, energy, communication, and governance, these systems deteriorate, illustrating the relentless pressure of entropy. Civilization as a battle against entropy. Civilization is essentially a complex system that resists disorder. Governments, education systems, legal frameworks, and technology act to organize human activity, coordinate resources, and reduce social and informational entropy. Yet history is full of examples where entropy prevails. Empires collapse, cities decay, knowledge is lost, and social order erodes. These are not failures of humanity, but consequences of universal entropic laws. Without continual energy, effort, and adaptation, all systems tend toward disorder. Technological efforts to preserve order. Technology represents one of humanity's most sophisticated strategies to resist entropy. Power grids, transportation networks, communication systems, and digital information require constant energy to maintain. Each technological innovation is a temporary reduction of entropy, allowing localized order to persist. Digital storage, for example, preserves knowledge but is subject to decay, obsolescence, and failure. Data centers require cooling, maintenance, and backup systems to function. In every case, human effort transforms energy into order, delaying the inevitable rise of disorder. This ongoing struggle highlights humanity's unique capacity to manage entropy consciously and strategically. Knowledge as an entropic tool. Knowledge, like energy, is subject to entropic forces. Without active preservation, information fades, memory decays, and societal understanding diminishes. Libraries, archives, and digital databases are human attempts to maintain low-entropy informational structures. However, knowledge is not static. Even as disorder acts upon it, new insights, inventions, and discoveries emerge from interactions with the entropic world. Chaos and uncertainty are not purely destructive. They stimulate creativity, adaptation, and innovation. Humanity thrives by navigating disorder and extracting meaningful patterns from it. Energy and human survival at its most fundamental level. Humanity's survival depends on energy management. Life itself is a localized battle against entropy. Cells maintain structure, replicate DNA, and perform metabolic processes to resist decay. On a societal scale, energy fuels agriculture, industry, and technology, sustaining civilizations, structures, deficits, resource depletion, and environmental stressors are examples of entropy's encroachment. They demonstrate that maintaining order is an ongoing effort, requiring foresight, planning, and adaptation. Humanity's capacity to harness energy effectively is a direct gauge measure of its ability to resist entropic pressures, cultural and social. Entropic culture and social systems also face entropic forces. Languages evolve, traditions fade, and historical knowledge can be lost. Cultural entropy is not purely negative. It drives the evolution of art, literature, science, and philosophy. Novelty and adaptation emerge from the interplay of order and disorder. Social structures that fail to adapt to changing conditions eventually succumb to entropy. While flexible, resilient societies can persist for millennia. Entropy ensures that no culture remains static. Change is inevitable, and adaptation is essential for survival. Humanity and the arrow of time. Entropy defines the arrow of time. And humanity experiences this flow in every aspect of existence. Growth, aging, memory, and civilization's rise and fall all follow the direction of increasing disorder. Time's passage is inseparable from entropy, linking human experience to universal laws, the impermanence of human life. Achievements and civilizations emphasizes the temporary nature of all order. Every creation, from art to technology, is a transient counterbalance to the inexorable rise of entropy. Recognizing this reality can foster both humility and awe, highlighting the significance of every human endeavor. Local reductions of entropy despite universal tendencies. Humans are remarkably effective at creating pockets of order. Cities flourish, knowledge is accumulated, and culture evolves. Each act of organization, whether building infrastructure, solving problems, or preserving information, is a temporary reduction of entropy. These localized reductions do not violate universal laws. They merely delay the inevitable. They demonstrate that while entropy governs the universe as a whole, intelligent systems can manage disorder locally, producing meaningful and lasting impact in the short term. Civilization as a dynamic, entropic system. Human civilization is not a static structure, it is a dynamic system in constant flux. Cities rise and fall, political institutions evolve, and cultures adapt to changing environmental, economic, and social conditions. Each of these systems requires energy, effort, and information to maintain order against the pervasive influence of entropy. For example, urban infrastructure, roads, bridges, water systems, and electricity networks requires ongoing maintenance. Without intervention, deterioration occurs naturally due to physical wear, material degradation, and environmental factors. Entropy ensures that no city can remain perfectly intact indefinitely, highlighting the continuous labor required to sustain human order. Technology, humanity's tool against disorder. Technology magnifies humanity's capacity to resist entropy. From simple tools to complex machines, technology enables humans to manage energy, organize information, and maintain structured systems more efficiently. Digital technologies are especially illustrative. Data centers, cloud computing, and artificial intelligence allow societies to preserve knowledge, analyze patterns, and make informed decisions. However, these systems are not immune to entropic forces. Hardware wears down, software becomes outdated, and networks are vulnerable to failures and cyber threats. Each technological advancement is a temporary reduction of disorder, requiring constant energy and attention to sustain. Energy, entropy, and sustainability. Energy is the lifeblood of human civilization. Every reduction of entropy, whether in infrastructure, knowledge, or daily life, requires energy. Food production, transportation, communication, and healthcare all consume energy to maintain local order. The laws of thermodynamics dictate that energy transfer is never perfectly efficient. Some energy is always lost as heat, contributing to overall entropy. Consequently, humanity must continually harness and manage energy to sustain civilization. Renewable resources, efficient energy storage, and sustainable practices are critical strategies to extend humanity's ability to resist entropic decay, knowledge preservation, and information systems. Humanity's ability to store, transmit, and utilize knowledge is one of its most powerful tools against entropy. Libraries, archives, digital databases, and educational institutions all serve as mechanisms to reduce informational disorder. By codifying knowledge, societies delay the inevitable loss of information and maintain continuity across generations. Yet these systems are not perfect. Books decay, digital formats become obsolete, and data can be corrupted or lost. Entropy ensures that even our most advanced knowledge systems require constant intervention and innovation to preserve their integrity. In this sense, humanity is engaged in an ongoing struggle to maintain order within the informational landscape. Social and cultural resilience, social and cultural systems are also entropic battlegrounds. Languages evolve, traditions fade, and social norms change under the influence of disorder. However, resilient societies cultivate adaptability, diversity, and redundancy to counteract this decay. Education. Legal frameworks, community networks, and cultural institutions act as stabilizing forces. They provide continuity, transmit knowledge, and help populations adapt to change. Just as technology combats physical decay, social systems resist disorder, demonstrating humanity's capacity to manage entropy on multiple levels. Crisis adaptation. And creativity. Entropy is not merely destructive, also drives adaptation and innovation. Crises such as natural disasters, economic collapses, or pandemics disrupt order but also catalyze creative responses. Societies and individuals develop new technologies, practices, and structures to manage chaos, turning disorder into opportunities for evolution and growth. In this way, entropy is a source of both challenge and progress. It forces humans to innovate, adapt, and reorganize, ensuring that life and civilization remain dynamic rather than static. Creativity and problem-solving are therefore local reductions of entropy generated through engagement with disorder, technology, and the limits of entropy management despite humanity's ingenuity. There are fundamental limits imposed by entropy. No system, biological, social, or technological, can resist disorder indefinitely. Even advanced civilizations will face degradation, resource depletion, and systemic failures. The ongoing digital revolution illustrates this tension. Cloud computing, artificial intelligence, and global networks expand humanity's capacity to manage information. But they also consume vast amounts of energy and create new forms of vulnerability. Maintaining order requires constant vigilance, adaptation, and investment. Entropy ensures that order is never permanent, only maintained temporarily through continuous effort. The human perspective on entropy. Understanding humanity's entropic context provides perspective on civilization and life itself. Our structures, knowledge, and technological achievements are remarkable precisely because they exist against the natural trend toward disorder. Every city built, every idea recorded, and every innovation realized represents a temporary triumph over universal decay. Entropy also encourages humility. It reminds us that all achievements are transient, and that survival, growth, and knowledge require ongoing effort. At the same time, it inspires awe. Humans have created extraordinary islands of order, demonstrating resilience, intelligence, and creativity in a universe governed by disorder. Humanity's struggle against entropy is ongoing, and the future presents both unprecedented challenges and opportunities. As populations grow, technology evolves, and our impact on the planet intensifies. Understanding entropy becomes critical to navigating the next stages of civilization. This final part explores how humans might continue to manage disorder, adapt to inevitable decay, and shape a sustainable future. The expanding challenge of entropy's human civilization becomes more complex. The entropic pressures we face also increase. Modern societies depend on intricate networks of energy, technology, and information. Every connection, from global supply chains to digital communication, introduces potential points of failure. Complexity brings vulnerability. Small disruptions, whether natural disasters, cyber attacks, or economic shocks, can propagate rapidly through interconnected systems. Entropy ensures that no system, no matter how sophisticated, can be perfectly stable. This reality highlights the importance of resilience, redundancy, and adaptability in maintaining order. Technological innovation as a response technology remains humanity's primary tool for managing entropy. Innovations in energy production, materials, science, computing, and artificial intelligence provide ways to preserve order, extend life, and enhance knowledge. Renewable energy sources, efficient storage systems, and smart infrastructure reduce the risk of systemic failure. Advanced computing and AI help organize information, predict risks, and optimize decision-making. Each technological advancement acts as a localized reduction of entropy, temporarily stabilizing complex systems. However, the energy cost of these interventions is high. Every act of order requires resources. Highlighting a fundamental truth, humanity can resist entropy, but it cannot escape the laws of physics, environmental pressures, and entropic feedback. Humanity's impact on the planet introduces additional entropic challenges. Climate change, resource depletion, and biodiversity loss are forms of ecological disorder exacerbated by energy consumption and population growth. Environmental entropy feeds back into human systems. Rising temperatures, extreme weather, and ecological collapse disrupt agriculture, infrastructure, and economies. Humanity must therefore manage not only internal disorder, but also the entropic consequences of its own actions. Sustainability is not merely a moral choice, it is an entropic necessity. Knowledge, adaptation, and predictive systems. One of humanity's most powerful defenses against entropy is knowledge. Scientific understanding, predictive modeling, adaptive planning allow societies to anticipate challenges and reduce uncertainty. For example, climate models, disaster simulations, and epidemiological forecasts are tools to manage entropic risk. They cannot eliminate disorder, but can mitigate its impacts, allowing localized systems to maintain order in the face of chaos. Knowledge becomes both a shield against decay and a guide for strategic adaptation. The role of consciousness and creativity. Human consciousness and creativity play a central role in resisting entropy. Imagination, problem-solving, and innovation transform random inputs and chaotic circumstances into structured solutions. Artists, engineers, scientists, and thinkers harness uncertainty to produce new forms of order, whether through technology, culture, or societal reform. Entropy, therefore, is not only a challenge, but also a catalyst for progress. The very unpredictability and disorder of the universe provide opportunities for creativity, adaptation, and transformation. Without entropy, innovation would be unnecessary. It is the dynamic tension between order and chaos that drives human achievement. Civilization as a continuous project. Humanity's future in an entropic universe is not predetermined. It is a continuous project. Maintaining civilization requires ongoing effort, energy, and vigilance. Education, governance, infrastructure, and cultural transmission are all mechanisms to preserve local order. Yet entropy ensures that no effort is permanent. Collapse, decay, and transformation are inevitable over long time scales. The challenge lies not in achieving permanence, but in sustaining order long enough to adapt, innovate, and evolve. Civilizations. Survival depends on its ability to continuously respond to entropic pressures, rather than attempting to eliminate them entirely. Ethical considerations in an entropic world. Entropy also raises profound ethical questions. With finite resources, energy constraints, and environmental limits, humanity must make choices about how to allocate effort to preserve order. Which systems, knowledge, and populations receive priority? How can energy and resources be managed to maximize resilience and reduce unnecessary disorder? These questions highlight the intersection of physics, society, and morality. Understanding entropy is not just a scientific endeavor. It informs how humans organize, govern, and plan for a sustainable future. The recognition of disorder as an inevitable force shapes ethical decision-making on local, global, and cosmic scales. The long-term perspective from a cosmic perspective. Humanity is a fleeting phenomenon, a temporary reduction of entropy on a small planet orbiting a modest star. Yet within this fleeting existence, humans have created remarkable order, cities, knowledge, technology, and culture. The future will continue to test humanity's ability to manage disorder. Population growth, resource limitations, and environmental change will increase entropic pressures. Success will depend on energy management, technological innovation, cultural adaptability, and the ability to harness creativity and intelligence to respond to unforeseen challenges. When we shift our perspective from human or planetary scales to the universe itself, entropy reveals its most dramatic, awe-inspiring, and unyielding expressions. The cosmos, from the smallest particles to the largest galactic structures, is an arena in which disorder relentlessly accumulates, shaping the destiny of stars, galaxies, and the very fabric of space-time. Entropy and the evolution of stars. Stars, the engines of cosmic energy, are inherently entropic systems. Their formation begins with clouds of gas and dust in a state of relative disorder. Gravity acts as a localizing force, pulling matter together to form dense cores where nuclear fusion ignites. For a star, this fusion is both a temporary defiance of entropy and a mechanism that accelerates it in the long term. Stars radiate energy outward, dispersing high-quality energy into the surrounding space while increasing the universe's overall entropy. Eventually, all stars exhaust their nuclear fuel, collapsing into white dwarfs, neutron stars, or black holes. In this life cycle, we witness entropy not only as a destructive force, but also as a natural driver of cosmic evolution, shaping the structure and fate of stellar systems. Galaxies and cosmic structures. Galaxies, composed of billions of stars. Gas, dust, and dark matter are also entropic systems. Over billions of years, gravitational interactions, star formation, and supernova explosions redistribute energy and matter, increasing the overall disorder of their environments. Yet, galaxies exhibit remarkable local order. Spiral arms, galactic cores, and star clusters represent islands of structure within a broader entropic flow. These patterns, however, are temporary, constantly reshaped by collisions, mergers, and internal dynamics. The universe, at this scale, demonstrates a delicate balance between chaos and organization. With entropy guiding its evolution, black holes, entropy extremes. Among the most striking examples of cosmic entropy are black holes. These regions of spacetime concentrate mass and energy to extreme densities, creating event horizons beyond which information cannot escape. Black holes epitomize entropic principles. They store vast amounts of information in highly compressed forms and act as engines of disorder by altering their surrounding environment. Hawking radiation further illustrates cosmic entropic processes. As black holes emit radiation and slowly evaporate, the information they contain is partially lost to the universe, highlighting the irreversible nature of entropy on an unimaginable scale. Black holes serve as cosmic reminders that no system, no matter how dense or extreme, is immune to disorder. The cosmic microwave background and Entropy. The cosmic microwave background, CMB, provides a snapshot of entropy in the early universe. This remnant radiation from the Big Bang reveals the distribution of matter and energy just after the universe's formation, showing fluctuations and irregularities that would later seed galaxies and large-scale structures. These primordial irregularities represent the early entropic tendencies of the cosmos. Over billions of years, the universe has evolved from a hot, dense, and highly energetic state to a colder, more diffuse, and entropic condition. Observing the CMB allows scientists to trace the arrow of time, the progression of disorder, and the unfolding of cosmic history. Dark energy, expansion and increasing disorder. Cosmic expansion, driven by dark energy, accelerates the universe's entropic trajectory. As galaxies drift apart, gravitational interactions decrease, and energy spreads over ever larger volumes. The universe becomes increasingly diffuse. Cold and disordered, a process sometimes referred to as heat death, where all energy gradients diminish and localized order becomes nearly impossible. This ultimate cosmic fate illustrates entropy on the grandest scale. Even the most massive structures, the most intelligent civilizations, and the most energetic events will eventually succumb to universal disorder. Entropy is not merely a local or human concern. It is the ultimate arbiter of cosmic destiny. Local reductions of cosmic entropy despite the overwhelming trend toward disorder. Localized reductions of entropy occur even on cosmic scales. Planetary systems, habitable zones, and potentially life-bearing worlds are temporary pockets of order. Stars provide energy gradients that allow chemistry, biology, and eventually consciousness to emerge, creating temporary islands of structured complexity in a vast, entropic sea. These localized reductions are fragile. Planetary environments are subject to stellar evolution, asteroid impacts, and cosmic radiation, illustrating the delicate balance required to maintain order amidst the entropic currents of the universe. Yet these islands of order are also the crucibles of intelligence, culture, and exploration phenomena that temporarily defy cosmic disorder. Cosmic perspective on humanity from this vantage point. Humanity and its civilizations are infinitesimal, yet significant manifestations of order in a universe dominated by entropy. Every achievement, from building cities to exploring space, exists as a fleeting counterbalance to the relentless march of disorder. Understanding cosmic scale, entropy fosters a profound perspective. Our efforts, knowledge, and ingenuity are temporary yet meaningful. We participate in the universe's natural processes, creating islands of order, preserving knowledge, and exploring patterns in the face of universal disorder. As we continue to explore entropy on cosmic scales, we must examine how it governs the formation, evolution, and eventual fate of the universe's largest structures. From the birth of stars to the behavior of entire galaxies and the extreme physics of black holes, entropic principles dictate the organization and eventual disorder of all cosmic phenomena. Stars as engines of cosmic. Entropist stars are perhaps the most vivid examples of entropy at work. While they may appear as stable, luminous bodies in the night sky, they are in a constant battle against disorder at both micro and macro scales. Inside a star, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy. This energy sustains the star structure and radiates into space, creating localized pockets of order. However, the star simultaneously generates entropy. Energy disperses, matter is converted, and the system gradually approaches thermal equilibrium. The life cycle of a star from nebular collapse to main sequence, red giant, and eventual collapse into a white dwarf. Neutron star or black hole illustrates entropy's dual nature. It enables complexity temporarily, while inevitably driving the system toward disorder. Galaxies. Islands of structure in a sea of chaos. Galaxies represent another level of entropic complexity. Billions of stars, gas clouds, and dark matter coalesce into intricate structures such as spiral arms, bulges, and halos. These patterns are highly ordered, but exist in a universe dominated by increasing disorder. Interactions between galaxies, such as collisions and mergers, redistribute energy and matter, accelerating the entropic evolution of these systems. Star formation, supernova explosions, and black hole activity all inject energy, heat, and radiation into the surrounding environment, increasing cosmic entropy. Despite their apparent stability, galaxies are not permanent. Over billions of years, their structures will gradually decay. Stars will exhaust their fuel, and the energy contained within them will disperse. The elegance we observe today is a temporary reduction of disorder in a constantly evolving system. Black holes. Concentrated entropy black holes exemplify entropy at its most extreme. These cosmic objects concentrate mass and information in extraordinarily dense points, warping space-time and creating event horizons from which nothing can escape. Hawking radiation demonstrates that black holes are not static. They slowly lose mass and energy over unimaginable timescales. This process converts highly organized matter into radiation, increasing the entropy of the universe. In effect, black holes act as both repositories and amplifiers of disorder. They also challenge our understanding of information and entropy. According to the laws of physics, the information about all matter that falls into a black hole must be conserved. Yet it becomes practically irretrievable. This paradox illustrates the profound interplay between order, disorder, and the limits of knowledge on a cosmic scale. Star clusters and local entropic interactions, smaller structures. Such as star clusters demonstrate how local entropic processes operate within larger systems. Stars and clusters interact gravitationally, exchanging energy and gradually dispersing over time. These interactions are governed by entropic principles. The more chaotic the system, the faster it evolves toward equilibrium. Even in these relatively small systems, we observe the balance of order and disorder. Clusters may form beautifully symmetric arrangements, but gravitational interactions, stellar evolution, and external forces ensure that these configurations are temporary. Entropy is relentless, shaping the structure and eventual dissolution of these systems. Cosmic expansion and increasing entropy, the accelerating expansion of the universe, driven by dark energy, exacerbates cosmic entropy. As space stretches, matter and energy become increasingly diffuse, and galaxies drift further apart. This expansion reduces the potential for gravitational interactions that create order, effectively making localized reductions of entropy such as star formation or planetary systems rarer over time. The universe moves toward a heat death, a state of maximum entropy, where energy gradients are minimal and all structures eventually decay. The implications are profound, even the most massive. Ordered systems are ultimately temporary. Stars burn out, galaxies disperse, and black holes slowly evaporate. Entropy dominates the cosmos, and localized order exists only fleetingly against this vast backdrop of disorder. Cosmic cycles of entropy. Despite this relentless increase in disorder, the universe exhibits cycles of local entropy reduction. Star formation, planetary development, and even the emergence of life represent temporary decreases in entropy. These cycles are powered by energy flow from stars, demonstrating that order can arise from disorder. Albeit briefly, these entropic cycles reveal a universe in motion. Pockets of order form, persist, and decay, giving way to new structures and processes. In this sense, entropy is not only a destructive force, but also a driver of cosmic creativity and complexity. Observing entropy across the cosmos, modern astronomy allows us to witness these entropic processes directly. Observations of supernova, black hole activity, galactic collisions, and cosmic microwave background fluctuations provide evidence of entropy shaping the universe at every scale. By studying these phenomena, scientists can trace the arrow of time, predict the evolution of cosmic structures, and understand how localized order arises and eventually succumbs to disorder. Entropy is not abstract. It is observable, measurable, and fundamentally intertwined with the life cycles of stars, galaxies, and black holes. As we conclude our exploration of cosmic entropy, it becomes evident that the universe itself is an entropic system, governed by principles that dictate its past, present, and eventual future. From the formation of stars to the expansion of space, entropy shapes every process, setting limits on the persistence of order and the potential for complexity. In this part, we examine the ultimate fate of the universe and the role entropy plays in its long-term evolution. The heat death of the universe. 1. Of the most widely discussed consequences of cosmic entropy is the concept of the heat death. This scenario describes a future in which the universe reaches a state of maximum entropy, with energy evenly distributed across space. In such a state, no energy gradients exist to drive physical processes. Stars burn out, black holes evaporate, and matter decays into increasingly uniform forms. All local order collapses, and the universe becomes a cold, dark, and nearly featureless expanse. Life as we know it would be impossible, as all processes that require energy differentials would cease. Heat death is the ultimate demonstration of entropy, the complete and irreversible transformation of usable energy into disorder. It illustrates that even the most massive, ordered systems, galaxies, stars, civilizations are temporary in the cosmic timeline. Black holes and the long term fate of entropy. Black holes play a unique role in this cosmic entropic narrative. Over unimaginably long timescales, even the most massive black holes will slowly evaporate via Hawking radiation. This process converts concentrated mass into radiation, further increasing the universe's entropy. Eventually, the universe will contain no stars, planets, or conventional matter, only diffuse particles, low energy, radiation, and the remnants of evaporated black holes. These final stages underscore the inexorable nature of entropic processes, where every structure and concentration of energy eventually succumbs to disorder. Cosmic inflation and entropy. Entropy also played a crucial role in the universe's earliest moments. The cosmic inflation period, rapid expansion, just after the Big Bang, set the stage for the distribution of matter and energy that allowed stars and galaxies to form, while inflation created pockets of local order from an initially chaotic state. It also amplified entropy on a cosmic scale. Tiny quantum fluctuations stretched across vast regions of space became the seeds for galaxies and large-scale structures. Entropy was both the force driving disorder and the mechanism enabling complexity to emerge. The arrow of time. Entropy defines the arrow of time, the unidirectional flow from order to disorder. On cosmic scales, this arrow is visible in the evolution of stars, galaxies, and the universe itself. Every process from nuclear fusion in stars to the evaporation of black holes advances the entropic clock. Time, as experienced by conscious beings, is inseparable from these entropic changes. The universe's history and its unfolding future are dictated by the inexorable increase of disorder, local order in a disordered universe. Even as the universe trends toward maximum entropy, local reductions of disorder continue to occur. Stars form, planetary systems develop, and life emerges on at least some worlds. These islands of order are temporary and fragile, but they allow for the existence of consciousness, culture, and knowledge. Understanding cosmic entropy provides perspective. Humanity's achievements are brief but meaningful. Life and civilization are remarkable because they arise as temporary defiance of universal disorder, shaped by the energy flows of stars and the structure of matter. Speculative futures and entropy. The future of cosmic entropy also invites speculation about advanced civilizations and their strategies to resist disorder. Could intelligent life harness black holes, manipulate energy, or stabilize local systems to extend order in the face of entropic decay? While such ideas remain theoretical, they highlight a fundamental truth. Entropy sets constraints, but within these constraints, complexity and creativity can flourish, albeit temporarily. Even in a universe trending toward heat death, localized systems may persist long enough to explore, observe, and perhaps even influence cosmic processes. Reflections on cosmic perspective from this vantage point. Human concerns, planetary conflicts, and even civilizations pale in comparison to the vast entropic universe. Yet our ability to understand, predict, and influence our local environments reflects the profound ingenuity that emerges in the presence of disorder. Entropy is not merely destructive. It is the framework within which all structure arises. Without the pressure of disorder, stars would not burn, galaxies would not form, and life could not emerge. Entropy is simultaneously the ultimate challenge and the engine of creation, driving both decay and complexity across the cosmos. Entropy is not only a scientific principle, but also a profound philosophical concept. Beyond thermodynamics, cosmology, and information theory, entropy invites reflection on the nature of reality, the passage of time, and the impermanence of all things. By examining entropy through a philosophical lens, we gain insights into human existence, ethics, and the meaning we assign to order and disorder in our lives. The inevitability of change. One of the central philosophical lessons of entropy is the inevitability of change. Everything in the universe trends toward disorder. Stars burn out, civilizations rise and fall, bodies age, and even thoughts and memories are subject to transformation over time. This universal principle challenges the human desire for permanence. Philosophers have long grappled with impermanence, from Heraclitus' assertion that everything flows to Buddhist teachings on the transience of existence. Entropy provides a scientific foundation for these observations, demonstrating that change is not only inevitable, but also deeply embedded in the structure of reality itself. Time, mortality, and the arrow of entropy defines the arrow of time, providing a framework for understanding past, present, and future. Time's direction is intimately linked to the progression of disorder. We remember the past because it had lower entropy than the present. And we anticipate the future, knowing that entropy will increase. This insight has profound implications for philosophy. It frames human mortality as part of a universal pattern, just as the universe evolves toward disorder. Individual lives are finite, temporary, and subject to decay. The awareness of entropy encourages reflection on the value of time, the choices we make, and the transient nature of our achievements. Order, meaning, and human creativity. Entropy also highlights the role of human creativity in generating temporary order. Art, science, architecture, and culture are all ways humans impose structure upon chaos. These acts are fleeting, yet they provide meaning and coherence in a world governed by disorder. Philosophically, this suggests that meaning is not inherent but constructed. Just as entropy is a natural process, our attempts to create order are a response to it. By embracing this dynamic, humans can find purpose not in permanence, but in the act of shaping, organizing, and interpreting the world around them. Ethics in an entropic world, the inevitability of disorder raises ethical questions. If all systems decay, how should humans prioritize effort, resources, and energy? Should our actions aim to preserve temporary order, maximize knowledge, or simply enjoy transient beauty? Entropy challenges conventional notions of value and permanence. Ethical frameworks may need to account for the finite and fragile nature of order, encouraging stewardship of life, knowledge, and the environment. Understanding entropy fosters humility, responsibility, and awareness of the broader consequences of our actions in a world that is ultimately impermanent. Entropy and existential philosophy. Existence explore themes closely aligned with entropy: the transience of existence, the search for meaning, and the confrontation with uncertainty. The recognition that life is temporary and that disorder is inevitable aligns with the existentialist emphasis on individual responsibility and authentic living. Entropy provides a scientific backdrop for existential reflection. It illustrates that while the universe is indifferent to human concerns, the human capacity for consciousness, creativity, and reflection enables a temporary resistance to disorder. In other words, humans can generate pockets of meaning and structure in an otherwise entropic cosmos. Entropy as a metaphor. Philosophers and thinkers often use entropy metaphorically to explore concepts beyond physics. Entropy can represent decay in societies, the fragility of relationships, the inevitability of personal change, or the loss of knowledge over generations. This metaphorical use bridges science and philosophy, showing that the principles governing particles and energy can illuminate human experience. Disorder becomes a lens through which we examine cultural decline, memory, innovation, and the impermanence of all systems. Entropy is not only a physical and philosophical principle, but also a crucial lens through which humans understand knowledge, learning, and the pursuit of truth. Our capacity to perceive, interpret, and organize information is inherently entropic. Disorder infiltrates memory, communication, and even reasoning. Yet human cognition is remarkable in its ability to create order, structure, and meaning despite these entropic pressures. The fragility of knowledge. All knowledge is vulnerable to entropy. Written records decay, digital information becomes corrupted, and oral traditions are altered over time. Even the human brain, the most complex storage system known, is subject to memory loss, error, and degradation. Entropy infiltrates understanding at every level. This fragility emphasizes the temporal nature of knowledge. No matter how carefully documented or transmitted, information exists in a constantly changing, disorder-prone environment. Awareness of this vulnerability encourages careful stewardship of knowledge, robust archiving systems, and redundancy in communication and education. Human understanding is a local reduction of entropy. Despite these challenges, human cognition acts as a localized counterforce to disorder. Learning, reasoning, and the scientific method enable individuals and societies to structure information, identify patterns, and predict outcomes. In effect, knowledge is a temporary reduction of entropy in the chaotic landscape of ideas. Every scientific discovery, philosophical insight, or technological breakthrough represents a small island of order in a sea of uncertainty. Yet, like all entropic reductions, these gains are temporary. Knowledge must be preserved, taught, and continuously refined to maintain its structure against the inexorable pressures of decay and misunderstanding. Science, entropy, and the pursuit of truth. Science embodies humanity's structured approach to understanding the universe. Experimental methods, mathematical modeling, and peer review act as mechanisms to manage informational entropy. By testing hypotheses, refining models, and correcting errors, scientists create systems of knowledge that are resilient. Though not immune to disorder, entropy ensures that no model or theory is permanent. Scientific understanding evolves. Paradigm shifts, such as the transition from Newtonian mechanics to relativity and quantum physics, illustrate that knowledge is provisional, always subject to refinement or replacement. Recognizing the entropic nature of understanding fosters intellectual humility and openness to new insights. Information, theory, and cognitive entropy. Information theory formalizes the concept of entropy in communication systems. Messages, signals, and data are all susceptible to noise and distortion. In human cognition, this translates to misinterpretation, forgetting, or misinformation by applying principles of redundancy, error correction, and structured encoding. Humans can reduce informational entropy. Writing, teaching, and digital archiving are examples of strategies designed to maintain clarity and preserve understanding across time and space. These mechanisms do not eliminate disorder, but mitigate its effects, allowing knowledge to persist in an inherently entropic environment. Creativity as entropy. Management creativity is a unique human response to entropy. Artists, writers, and innovators transform chaotic or ambiguous inputs into ordered expressions, whether through literature, music, visual art, or technological invention. Creativity channels the raw energy of uncertainty, imposing structure while embracing the dynamic and unpredictable nature of disorder. Philosophically, this suggests that human creativity is both a defense against and a product of entropy. Disorder provides the stimulus for innovation. Without challenges, unpredictability, or variation, there would be no need to create new solutions or forms. Entropy is, therefore, not merely an obstacle, but also a source of opportunity for human understanding, knowledge, transmission, and cultural resilience. Cultural systems, languages, traditions, educational structures act as entropic buffers, preserving knowledge across generations. Rituals, storytelling, and formal education reduce informational decay by providing repeated, structured reinforcement. Yet cultural knowledge is also entropic. Languages evolve, customs change, and histories are reinterpreted. Societies that recognize and actively manage these entropic pressures can sustain continuity, adaptability, and resilience. The study of entropy in knowledge and culture reveals the delicate balance between preserving order and allowing necessary adaptation. Philosophical reflections on entropic. Understanding entropy challenges the assumption that understanding is absolute or permanent. Instead, knowledge is provisional, context-dependent, and fragile. Philosophically, this encourages an attitude of humility, openness, and continuous inquiry. Understanding entropy fosters a perspective in which the pursuit of knowledge is valued not only for its outcomes, but also for the process itself. Human cognition and learning are part of the dynamic interplay between order and disorder, where the act of organizing, interpreting, and sharing information temporarily counteracts entropic decay. Entropy is more than a scientific or cognitive concept. It is intimately connected to the human quest for meaning. As the universe trends inexorably toward disorder, humans confront the transient nature of life, the fragility of relationships, and the impermanence of civilization. Philosophical engagement with entropy can help frame these existential challenges, guiding reflection on purpose, fulfillment, and the ways we create order in our personal and collective lives. Impermanence and the search for meaning. The recognition of entropy forces us to confront impermanence. Every moment, every achievement, every life is temporary, subject to the inexorable flow of disorder. This realization can evoke anxiety, yet it also offers profound insight. Meaning is not derived from permanence, but from engagement with the present. Philosophers from various traditions, Buddhist, Stoic, existential, have long emphasized the importance of accepting impermanence. Entropy provides a scientific framework for these teachings, showing that change and decay are universal. The pursuit of meaning, therefore, is less about resisting disorder and more about navigating it consciously, creating temporary pockets of order and significance. Human action as temporary order, every conscious action, from simple choices to ambitious projects, represents a momentary reduction of entropy. Building relationships, creating art, pursuing knowledge, and establishing institutions are all ways humans impose order on the chaotic flow of reality. Philosophically, this frames human existence as a constant negotiation with disorder. Purpose emerges not from permanence, but from the intentionality and care with which we shape our environments, ideas, and experiences. Life gains significance through these acts of ordering. However fleeting their effects may be, ethics in an entropic universe. Entropy also influences our ethical perspective. Awareness of disorder encourages reflection on responsibility, stewardship, and the consequences of action. Since all systems, including ecosystems, social structures, and human bodies, are subject to decay, ethical living involves maintaining order where possible. minimizing harm and nurturing resilience. From an entropic standpoint, morality can be seen as the conscious management of disorder, protecting fragile systems, preserving knowledge, fostering cooperation, and creating sustainable practices. By acknowledging impermanence, humans are motivated to act thoughtfully, balancing immediate needs with long-term consequences. Creativity, legacy, and the human spirit. Creativity is a powerful response to entropy. Art, literature, music, and innovation are ways of defying disorder, if only temporarily. These expressions leave traces that outlast the immediate moment, forming cultural and intellectual legacies that persist across generations. The human spirit, through creativity and exploration, demonstrates resilience against the encroaching tide of entropy, even knowing that all efforts are ultimately temporary. Humans strive to produce beauty, understanding, and connection, pockets of order that shine amid inevitable decay. Existential reflection and acceptance. Entropy invites existential reflection. Why act, create, or strive if all will eventually decay? Philosophical traditions suggest that meaning arises not from permanence, but from conscious engagement. Life is valuable not because it lasts forever, but because it exists, is experienced, and is shaped by intentionality. By accepting entropy as a fundamental aspect of reality, humans can cultivate a deeper appreciation for the fleeting beauty of existence. Awareness of impermanence fosters mindfulness, gratitude, and intentional action, transforming the awareness of disorder from a source of despair into a motivator for purposeful living. Entropy, consciousness, and awareness. Consciousness itself is an entropic system. Thoughts, perceptions, and memories are constantly in flux, shaped by the environment, biology, and experience. Awareness allows humans to temporarily resist disorder by learning, planning, reflecting, and creating. Individuals generate structured cognition and intentional behavior. Philosophically, consciousness represents humanity's unique capacity to confront entropy actively. While biological, cultural, and intellectual systems are ultimately temporary, conscious reflection allows us to understand, anticipate, and influence the flow of disorder, giving life intentionality and significance. The balance between order and acceptance. Living with entropy involves a balance between creating order and accepting impermanence. Excessive resistance to disorder can generate frustration and suffering, while complete surrender can lead to nihilism. Philosophical engagement with entropy encourages a dynamic equilibrium. Act to impose meaningful order where possible, while accepting the inevitability of change and decay. This perspective fosters resilience, creativity, and ethical awareness. Humans are empowered not by achieving permanence, but by navigating impermanence skillfully, producing temporary islands of structure, beauty, and understanding in an ever-changing universe. Entropy, often associated with cosmic phenomena or abstract scientific principles, is also deeply relevant to our everyday lives, while it governs the decay of stars and the evolution of galaxies. It equally shapes our personal environments, routines, and psychological experiences. Recognizing entropy in daily life can enhance mindfulness, organization, creativity, and emotional resilience. Understanding daily entropy. Daily life is filled with examples of entropy in action. Clothes get wrinkled, dishes pile up, electronic devices degrade, and schedules become disordered. These small, persistent forms of disorder can evoke frustration, but they are a natural reflection of the universe's tendency toward chaos. Understanding that disorder is inevitable allows individuals to approach daily challenges with perspective. Instead of fighting entropy as an enemy, one can accept its presence, plan around it, and even harness it as an opportunity for reflection and creativity. Time management and entropy. Time itself is an entropic force in our daily routines. Tasks left undone tend to accumulate, and responsibilities grow increasingly complex if not addressed. Procrastination and neglect amplify disorder, while proactive engagement reduces it by framing time management in entropic terms. We can better appreciate the necessity of prioritization, scheduling, and structured habits. Completing tasks, organizing spaces, and maintaining consistent routines are temporary reductions of disorder that enhance efficiency, clarity, and personal well-being. Physical spaces and entropic maintenance. Our physical environments are constant reminders of entropy. Homes, offices, and public spaces naturally drift toward disorder if neglected. Dust accumulates, objects scatter, and infrastructure deteriorates. Maintaining order in physical spaces is not about achieving permanent perfection and impossible goal, but about consciously applying effort to counteract the natural drift toward chaos. Regular cleaning, organization, and upkeep are practical strategies for managing entropic pressures, creating environments conducive to focus, relaxation, and comfort. Emotional and psychological entropy also operates on mental and emotional levels. Thoughts can become scattered, feelings can spiral, and stress can accumulate, reflecting the inherent disorder of complex psychological systems. Mindfulness practices, journaling, meditation, and reflective routines act as tools to manage emotional entropy. By consciously observing and structuring thoughts and emotions, individuals create temporary clarity and stability. These practices do not eliminate the underlying entropic tendencies of the mind, but they provide resilience and guidance in navigating disorder, creativity, and the flow of disorder. Interestingly, entropy is also a catalyst for creativity in daily life. Disorder introduces novelty, challenges, and unpredictability, all of which stimulate innovation and problem-solving. Artists, writers, and innovators often rely on entropic stimuli and unexpected occurrences, disruptions of routine or chaotic inputs to spark new ideas. Recognizing entropy as both a challenge and a resource allows individuals to harness disorder creatively, turning everyday unpredictability into opportunities for growth and expression. Social interactions and entropic dynamics. Human relationships are inherently entropic. Misunderstandings, conflicts, and evolving personalities introduce disorder into social networks. Maintaining meaningful connections requires effort, communication, and adaptation. Temporary reductions of social entropy by viewing relationships through an entropic lens. Individuals can cultivate patience, empathy, and resilience. Conflict and disorder are natural, but conscious engagement, compromise, and attentive care can stabilize and enrich interpersonal dynamics, creating lasting value even in an inherently unstable system. Financial and organizational entropy. Financial systems and personal organization are also subject to entropic forces. Budgets, schedules, and plans degrade without monitoring and adjustment. Entropy manifests as overspending, missed deadlines, cluttered workspaces, and chaotic routines. Regular review, planning, and adaptation act as practical interventions against these forms of disorder. Structured processes, reminders, and organization systems temporarily reduce entropic drift, improving efficiency, security, and clarity in both personal and professional life. Small actions, big impact. Daily life illustrates that even minor interventions can counteract entropy effectively. Cleaning a desk, responding to an email, organizing a shelf, or setting a schedule may seem trivial, but cumulatively, these actions maintain order against a background of inevitable disorder. Understanding entropy in this context encourages proactive behavior. Rather than resisting the natural tendency of things to become disordered with frustration, individuals can focus on consistent, deliberate actions that preserve order and enhance quality of life. While entropy is an inevitable force, humans have developed a multitude of strategies to manage, mitigate, and even leverage it in daily life. Recognizing the presence of disorder is the first step. The second is actively implementing practices that maintain temporary order, promote well-being, and enhance efficiency. In this part, we explore practical approaches to confronting entropy in everyday environments, tasks, and habits. Routine and habit formation. Establishing routines is one of the most effective ways to counteract daily entropy. Regular habits provide structure, reducing cognitive load and minimizing the disorder that can arise from inconsistent behavior. For example, a morning routine that includes waking up at a set time, preparing a nutritious meal, and planning the day's priorities creates stability. Habits like cleaning before bed, setting aside time for reflection, or scheduling exercise sessions act as systematic interventions against disorder. Routines function as predictable scaffolding, allowing humans to navigate the complexities of life while conserving energy and attention. They create temporal pockets of order, enabling individuals to respond effectively to the inevitable chaos of daily events. Physical, organization, and environmental maintenance. Our physical environments are highly susceptible to entropy. Clutter, disorganization, and neglect accumulate over time. Counteracting this requires deliberate action, tidying spaces, arranging objects logically, and removing unnecessary items. Even small interventions, sorting mail daily, keeping frequently used items accessible, or cleaning a kitchen after each use can significantly reduce the perceived burden of disorder. The key is consistency. Regular maintenance prevents minor disorder from escalating into overwhelming chaos. Applying the principle of entropy awareness to physical spaces transforms mundane chores into meaningful acts. Each effort is a temporary reduction of disorder, creating environments conducive to focus, calm, and productivity. Task management and prioritization. Tasks left unattended increase cognitive and emotional entropy. Procrastination allows responsibilities to pile up, creating mental clutter and stress. Effective task management, therefore, acts as a counterbalance to daily disorder. Techniques such as the Eisenhower matrix, distinguishing urgent from important tasks, time blocking, and setting achievable goals provide structured approaches to reduce mental entropy. By dividing complex projects into smaller, manageable actions, individuals maintain order in workflows and prevent overwhelming accumulation of tasks. Digital entropy and information management. Digital life is another domain where entropy is highly visible. Emails, files, digital photos, and social media notifications accumulate rapidly, creating cognitive overload. Organizing digital information through folders, tagging, backups, and automated routines is critical to preserving clarity. Regular digital decluttering old emails, cleaning desktop files, and uninstalling unused applications acts as a digital equivalent of housekeeping. These actions reduce the disorder in our virtual environments, improving efficiency and reducing the stress associated with information overload. Emotional and psychological resilience. Psychological entropy manifests as scattered thoughts, emotional volatility, and stress accumulation. Mindfulness practices, meditation, journaling, and cognitive reflection help manage these internal forms of disorder. Structured reflections, such as listing priorities, evaluating emotional responses, or identifying patterns of thought, creates temporary mental clarity. Engaging in creative activities, exercise, and social interaction also provides channels to stabilize emotional fluctuations, transforming chaotic internal states into balanced, productive experiences. Financial management. Financial systems are vulnerable to entropic pressures. Unmonitored spending, missed bills, and neglected investments can lead to disorder and instability. Maintaining financial order requires consistent tracking, budgeting, and periodic review. Tools like automated bill payments, spreadsheets, and budgeting apps act as interventions against financial entropy. By structuring income, expenses, and savings, Individuals create temporary order in a domain that naturally tends toward disorder, reducing stress and enhancing long-term security, social and relational. Entropy relationships naturally experience entropic pressures through misunderstandings, evolving personalities and external stressors. Conscious communication, empathy, and regular engagement reduce relational disorder. Simple actions: checking in with friends, resolving conflicts early, and creating shared experiences act as stabilizing forces in social networks. By acknowledging the entropic nature of interactions, individuals can proactively cultivate meaningful and resilient relationships, embracing disorder as a catalyst. Interestingly, not all entropy is detrimental. Disorder often introduces novelty, challenge, and opportunity. Random events, unexpected problems, and disruptions can stimulate creativity, problem-solving, and personal growth. Viewing entropy as a potential source of opportunity encourages flexibility and adaptive thinking. When handled constructively, moments of disorder can inspire new solutions, enhance resilience, and enrich the complexity of life experience. Integrating entropy awareness into daily life. Incorporating entropy awareness involves a dual approach. Accept the inevitability of disorder while actively implementing strategies to maintain temporary order. Key practices include routine and habit formation. Establish predictable structures in daily life. Environmental maintenance. Organize and clean physical and digital spaces regularly. Task prioritization. Use structured methods to manage responsibilities. Mindfulness and reflection stabilize mental and emotional states. Financial and relational stewardship maintain clarity and reduce disorder in personal systems. Creativity and adaptation harness disorder as a source of novelty and growth. By consciously applying these strategies, individuals experience a reduction in stress, increased clarity, and enhanced well-being. Entropy remains inevitable, but daily life becomes more manageable, purposeful, and fulfilling. Daily life is an intricate interplay between order and disorder, stability and unpredictability. Philosophically, entropy invites reflection on how humans perceive, interact with, and derive meaning from the patterns and chaos that surround them. Understanding the entropic nature of daily life provides a framework for mindful engagement, ethical awareness, and personal growth. Impermanence in the everyday. Entropy reminds us that all systems, personal habits, possessions, relationships, and routines are inherently temporary. Nothing remains perfectly ordered for long. Furniture gathers dust, commitments shift, friendships evolve, and emotions fluctuate. Acknowledging this impermanence encourages a balanced perspective. It fosters acceptance of minor failures, setbacks, or disruptions as natural elements of existence. Philosophically, this echoes teachings from Stoicism and Buddhism. By recognizing the transient nature of all things, individuals can cultivate equanimity, patience, and resilience in daily life. Finding meaning in temporary order while permanent control over disorder is impossible. Humans can create temporary pockets of order, and within these moments, meaning emerges. Organizing a workspace, completing a project, or tending to relationships provides a sense of purpose and accomplishment. Entropy teaches that meaning is constructed, not inherent. Every act of order, no matter how fleeting, represents a conscious engagement with life, transforming otherwise chaotic experiences into purposeful actions. Recognizing the value of these temporary islands of stability enhances satisfaction and mindfulness. Ethical implications of daily anthropic awareness also shapes ethical considerations. Decisions about resource use, social behavior, and personal responsibility are influenced by an understanding of disorder. For instance, maintaining cleanliness, reducing waste, and respecting shared spaces are ethical responses to the inevitability of decay and disorder. Similarly, attending to social relationships, emotional well-being, and communal responsibilities reflects conscious effort to counteract relational entropy. Philosophically, ethical behavior can be seen as active stewardship against disorder, promoting stability and well-being for oneself and others. Time, choice, and entropy. Time is a subtle but powerful entropic force in daily life. Procrastination, delay, and neglect amplify disorder, whereas deliberate action, planning, and prioritization reduce it. Philosophically, this underscores the importance of intentionality. Each choice to act thoughtfully is a counterforce to the natural drift toward chaos. By engaging with the flow of time consciously, humans assert agency in shaping their personal and professional environments, creating structure amidst the inevitable progression of disorder. Emotional awareness and reflection. Entropy is not limited to physical or social systems, it permeates the mind. Thoughts scatter, emotions fluctuate, and stress accumulates. Mindful reflection, journaling, and emotional regulation act as philosophical and practical responses to this. Internal disorder, acknowledging the entropic nature of mental life, cultivates acceptance and self-compassion. Rather than resisting natural fluctuations or judging oneself harshly, individuals can observe patterns, respond constructively, and maintain balance. This reflective approach transforms psychological entropy from a source of frustration into a vehicle for growth and self-awareness, creativity. And adaptation. Disorder is often a catalyst for innovation and creativity. In daily life, unplanned events, unexpected challenges, and minor disruptions stimulate problem-solving, adaptability, and imaginative thinking. Philosophically, this illustrates that entropy is not purely destructive. It provides the raw material for transformation, learning, and evolution. By embracing unpredictability, individuals can discover novel solutions, adapt to new circumstances, and enrich personal experiences. Disorder becomes a teacher, offering lessons in flexibility, resilience, and resourcefulness, integrating entropy awareness into life philosophy. Living with an entropic perspective encourages a dynamic approach to everyday existence. Key philosophical reflections include acceptance of impermanence. Understand that disorder is natural and inevitable. Meaning in temporary order. Value the small acts that create structure and purpose. Ethical engagement. Respond to disorder responsibly in social, environmental, and personal contexts. Intentional action. Use time and choices wisely to counteract entropic drift. Mindful adaptation. Observe internal and external fluctuations without resistance. Creativity from chaos. Leverage unpredictability as a source of innovation and growth. By integrating these reflections, daily life becomes a practice of conscious engagement with entropy, transforming routine existence into a meaningful, mindful, and ethically grounded journey. Closing thoughts for Part 3. Entropy in everyday life is unavoidable, yet it need not be a source of despair. Recognizing the presence of disorder encourages mindful action, intent, and ethical awareness. Philosophical reflection on daily entropy reveals that value and meaning arise not from permanence, but from engagement. Every small act of order, thoughtful decision, and adaptive response contributes to a richer, more resilient life experience. Ultimately, by understanding and embracing entropy in daily existence, humans can navigate the balance between chaos and order, cultivating clarity, purpose, and well-being amid the natural unpredictability of the world. As we drift through life, sleep, and thought, entropy surrounds us, shaping the cosmos, our minds, and even the smallest moments of daily life. Understanding it reminds us of the delicate balance between order and chaos, impermanence and creation. Even as disorder is inevitable, every action, thought, and decision becomes a small rebellion against entropy, a way to craft meaning in a universe that constantly shifts. So, as you rest and reflect tonight, remember the universe may trend toward chaos. But within you lies the power to create islands of order, beauty, and insight. Sleep peacefully, knowing that even in disorder, there is purpose.